Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold reaches beyond Neptune, where a visitor from another star system moves through our sun's invisible breath. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The comet designated 3Y/Atlas enters the inner solar system in late 2024, moving at 29 kilometers per second relative to the Sun. It carries with it the chemistry of a stellar nursery that collapsed 4.5 billion years ago, somewhere in the spiral arm of the Milky Way, perhaps 200 light-years from here, perhaps more. No one knows precisely which star system birthed this traveler. The designation 3Y marks it as the third confirmed interstellar object detected passing through our cosmic neighborhood, a wanderer among wanderers, unbound by the Sun's gravity, following a hyperbolic trajectory that will carry it back into the galaxy's dark spaces once its brief visit concludes. Only took 4,500 million years to arrive. The comet measures perhaps 1 kilometer across, perhaps less. Ground-based telescopes capture its faint glow as sunlight reflects from a growing cloud of gas and dust. This coma, the diffuse atmosphere surrounding the nucleus, expands slowly as solar radiation warms frozen volatiles embedded in the comet's ancient ice. Water molecules sublimate directly from solid to vapor. Carbon monoxide follows. Dust grains, some no larger than particles of smoke, lift gently away from the surface, released from the gravitational grip of a body whose mass barely registers on cosmic scales. Spectroscopic analysis reveals the presence of cyanogen and diatomic carbon in the coma. These molecules fluoresce in ultraviolet light, painting the comet in wavelengths invisible to human eyes, but visible to spacecraft instruments that watch patiently from Earth orbit. The composition suggests formation in a cold outer disk, far from the light and heat of the parent star, ice condensed in temperatures hovering near absolute zero. Organic compounds assembled in darkness. For billions of years, this object drifted through interstellar space, absorbing perhaps a few cosmic ray impacts per century, accumulating a thin mantle of radiation-processed material on its surface. The comet does not hurry. Its velocity, though immense by terrestrial standards, places it among the slower interstellar visitors. Previous objects, 1I/Oumuamua and 2I/Borisov, pass through more quickly, suggesting different ejection mechanisms from their birth systems. 3I/Atlas may have been nudged gently from its home rather than flung violently. Gravitational interactions with a distant giant planet. Perhaps, or the slow erosion of orbital stability over geologic time. The galaxy contains billions of such objects, drifting in the space between stars, invisible until they happen to pass close enough to a solar system to reflect light. Somewhere near the orbit of Jupiter, the first tendrils of solar wind begin to interact with the comet's growing coma. Charged particles streaming outward from the Sun at 400 kilometers per second encounter neutral atoms evaporating from the nucleus. Collisions occur, electrons strip away. Water molecules become ions, electrically charged, no longer neutral. Suddenly responsive to magnetic fields embedded in the wind, this process happens continuously, quietly, without fanfare. Every second, perhaps 10 to the 24th molecules join the ionized tail. Every second, the comet loses a small fraction of its mass to space, never to be recovered. The solar wind itself remains invisible, No telescope can photograph it directly. Scientists infer its presence through indirect observation, the bending of comet tails, the aurora on Earth. The particle counts registered by spacecraft sailing through interplanetary space. The wind consists primarily of protons and electrons, with trace amounts of helium nuclei and heavier ions. It flows outward in all directions, filling the solar system with a tenuous plasma that extends far beyond the orbit of Pluto, creating a bubble called the heliosphere that separates the Sun's domain from the interstellar medium beyond, between the Sun and 3y/Atlas. Approximately 5 astronomical units of space contain this streaming plasma. An astronomical unit measures the distance from Earth to the Sun, roughly 150 million kilometers. 5 astronomical units stretches the imagination. Light crosses this distance in 41 minutes. The solar wind, moving at a small fraction of light speed, takes 4 days to traverse the same gap. Information about conditions at the Sun's surface reaches the comet with this delay, always lagging, always carrying news of the past. The comet does not know it is being watched. Ground stations track its position nightly. Amateur astronomers in dark sky locations photograph its faint glow. Space agencies consider trajectory calculations, wondering if any existing spacecraft might intercept it for close-range study. The numbers do not favor a rendezvous. 3I/Atlas follows an orbital plane tilted relative to the ecliptic, the flat disk in which Earth and the other planets orbit. Matching its trajectory would require fuel expenditures no mission currently in flight can afford. The comet will pass, be observed from a distance, and depart, leaving behind only photons and spectroscopic data. Only took 400 years of telescopic astronomy to spot the third one. No one can say with certainty what the comet's nucleus looks like up close. Models suggest a surface covered in dark, carbon-rich material, the residue of radiation processing and impacts with micrometeorites during its long interstellar journey. The ice beneath this crust may be pristine, unchanged since the comet's formation, or it may be layered, recording multiple phases of heating and cooling as the object passed through varying densities of interstellar gas. Core samples would reveal this history, but no core samples will be taken. The comet passes as a mystery, partially solved, partially preserved. Scientists debate whether 3I/Atlas possesses a magnetic field of its own. Most comets do not. They are too small, their cores too cold, to sustain the convective processes that generate magnetism in larger bodies. Yet the interaction between the solar wind and the comet's ionized coma creates temporary magnetic structures, draped field lines that wrap around the comet like cloth blown against a statue. These fields exist only in motion, only in the flow of plasma around an obstacle. Remove the solar wind, and they vanish. The sky above the comet's nucleus holds no stars, not invisible light. The coma scatters sunlight, creating a faint glow that drowns out distant stellar photons. Dust particles drift slowly upward, following trajectories shaped by solar radiation pressure and the weak gravity of the nucleus. Some grains escape entirely, others fall back, accumulating in different locations, redistributing mass across the surface. Over centuries, this process could alter the comet's rotation rate, though no one will be watching long enough to measure such changes. Somewhere in the comet's interior, ice older than Earth's oceans remains frozen, water molecules arranged in crystalline lattices, locked in place by temperatures that never rise above 100 Kelvin. This ice remembers nothing. It has no memory. But it carries isotopic ratios, the relative abundances of hydrogen, oxygen, carbon, nitrogen, that encode information about the chemistry of its birth cloud. When the ice finally evaporates, those ratios will be measured, compared to comets born in our own solar system, and used to constrain models of star formation in other parts of the galaxy. The comet moves through the calm before the gust. Solar activity remains low. No major coronal mass ejections disturb the steady flow of wind. The Sun's magnetic field, though complex, holds a relatively stable configuration. This will not last. The Sun breathes in cycles, and the current breath nears its end. Already, observers note small increases in sunspot counts, faint harbingers of the coming solar maximum when the wind will grow turbulent, when magnetic storms will ripple through interplanetary space with renewed intensity. For now, though, the wind flows smooth. 3. I/Atlas drifts inward, wrapped in its growing coma, trailing ions that stream away in a tail millions of kilometers long. The tail points always away from the Sun, shaped not by the comet's motion, but by the pressure of light and the flow of charged particles. In this way, the comet becomes a wind vane, a visible marker of invisible currents that fill the space between worlds. Only took one small frozen traveler to make the invisible briefly visible. The Sun loses mass continuously, every second. Approximately 1 million tons of material streams away from its surface in the form of solar wind. This mass consists primarily of protons, hydrogen nuclei stripped of their electrons, and free electrons, with smaller quantities of helium ions and trace elements forged in the Sun's core through nuclear fusion. The wind does not flow uniformly. It emerges from the Sun's corona, the outermost layer of the solar atmosphere, where temperatures exceed 1 million Kelvin despite the surface below measuring only 5,700 Kelvin. No one fully understands why the corona is so hot. Theories invoke magnetic reconnection, acoustic waves, and turbulent heating mechanisms. But the precise energy transfer process remains uncertain. What is certain is that this extreme temperature accelerates particles to escape velocity, allowing them to overcome the Sun's gravitational pull and flow outward into space. The wind carries with it the Sun's magnetic field, frozen into the plasma through a phenomenon called flux freezing. Where the plasma goes, the field lines follow, stretching outward like elastic threads attached to a rotating sphere. The solar wind divides into two regimes, slow and fast. Slow wind emerges from the Sun's equatorial regions and from the boundaries of coronal holes, traveling at roughly 300 to 400 kilometers per second. Fast wind originates in coronal holes themselves, regions where the Sun's magnetic field lines extend directly into space rather than looping back to the surface, and achieves speeds of 700 to 800 kilometers per second. These two wind types carry different chemical compositions, different temperatures, different magnetic field geometries. Only took 60 years of space-age observations to map these differences. At the distance of 3 I/Atlas, approximately 5 astronomical units from the Sun, both wind types have undergone substantial evolution. The fast wind, launched from coronal holes at high speed, maintains much of its velocity, but has cooled through adiabatic expansion. The slow wind, though initially cooler, has been compressed and heated by interactions with faster streams overtaking it from behind. These stream-stream interactions create regions of enhanced density and pressure that ripple through the inner heliosphere like waves on a pond. Though the pond measures billions of kilometers across and the waves take days to pass, the magnetic field embedded in the wind possesses a complex structure. Near the Sun, field lines emerge radially, pointing straight outward from the surface, but the Sun rotates once every 27 days at its equator, faster than the wind flows outward. This rotation twists the field into a spiral pattern, the Parker spiral, named after Eugene Parker, who predicted the existence of the solar wind in 1958 before any spacecraft had measured it directly. The spiral angle increases with distance from the Sun. At Earth's orbit, 1 astronomical unit, the field makes an angle of about 45 degrees to the radial direction. At 5 astronomical units, near Jupiter and the current position of 3 I/Atlas, the angle approaches 65 degrees. The field lines do not exist in isolation. They connect regions on the Sun's surface to locations throughout the heliosphere, creating invisible pathways along which particles can travel. Electrons, being lighter and more mobile than protons, stream along these field lines with relative ease, carrying electrical currents that help maintain quasi-neutrality in the plasma. The currents themselves generate secondary magnetic fields, adding layers of complexity to the overall structure, between field lines of opposite polarity. Thin current sheets form regions where the magnetic field reverses direction over very short distances. The largest of these sheets, called the heliospheric current sheet, extends throughout the solar system like a vast, warped surface separating regions of opposite magnetic polarity. The sheet oscillates above and below the solar equator, its shape reflecting the tilt of the Sun's magnetic dipole axis and the distribution of magnetic flux on the solar surface. Spacecraft crossing this sheet measure abrupt changes in field direction, density variations, and shifts in electron temperature. Only took missions to the outer solar system to reveal how far the current sheet extends. The solar wind does not flow smoothly. Turbulence develops as faster streams interact with slower ones, as magnetic field lines tangle and reconnect, as pressure gradients drive instabilities in the plasma. This turbulence cascades across a vast range of spatial scales, from millions of kilometers down to the ion gyroradius, the tiny circular path an ion traces as it spirals around a magnetic field line. At the largest scales, turbulence manifests as large amplitude fluctuations in velocity and magnetic field. At the smallest scales, it appears as rapid oscillations that dissipate energy through collisionless processes not yet fully understood. The wind carries information about the Sun's interior. Elemental abundances in the wind reflect the composition of the corona, which in turn reflects the composition of the Sun's outer layers. Isotopic ratios provide clues about nuclear processes occurring in the core. The charge states of heavy ions, oxygen, silicon, iron, indicate the temperature and density conditions in the regions where the wind originates. By measuring these properties at multiple locations throughout the heliosphere, scientists reconstruct a picture of the Sun's atmosphere and its complex, time-varying structure. Spacecraft scattered through the inner solar system monitor the wind continuously. Parker Solar Probe, launched in 2018, dives repeatedly into the Sun's corona, measuring conditions closer to the Sun than any previous mission. Solar Orbiter, a joint NASA-ESA mission, observes the Sun from varying distances and latitudes, building three-dimensional maps of the wind's structure. These spacecraft send data back to Earth at regular intervals, their transmissions traveling at the speed of light, arriving minutes or hours after the measurements are taken. 3I/Atlas moves through this wind unaware of the spacecraft, unaware of the measurements, unaware of the elaborate structure surrounding it. The comet responds only to local conditions, the density of plasma in its immediate vicinity, the strength of the magnetic field threading through its coma, the pressure of solar radiation on its dust grains. These local conditions, in turn, depend on the global structure of the heliosphere, on events occurring 93 million miles away at the Sun's surface, on the slow rotation of coronal holes and the unpredictable emergence of active regions. The wind does not push the comet sideways. Its momentum flux is far too small to alter the comet's trajectory, but it does sculpt the comet's tail, constraining the flow of ionized gas into a narrow beam that extends millions of kilometers downstream. This tail, visible in ultraviolet images, glows with emission from carbon monoxide ions and other molecular fragments. The glow fluctuates in response to changes in the wind's density and velocity, creating a time-varying record of solar wind conditions encoded in the tail's brightness and structure, only took one interstellar visitor to provide a natural probe of solar wind properties at 5 astronomical units. Models of the interaction between 3I/Atlas and the solar wind rely on magnetohydrodynamic equations, mathematical descriptions of how electrically conducting fluids behave in the presence of magnetic fields. These equations, first formulated in the mid-20th century, govern the coupling between plasma flow and electromagnetic forces. Solving them for the complex geometry of a comet-wind interaction requires computational resources unavailable to earlier generations of scientists. Modern simulations run on supercomputers, dividing space into millions of grid cells and evolving the plasma properties forward in time using numerical methods refined over decades of research. The simulations predict that a bow shock should form upstream of 3I/Atlas if the comet's outgassing rate exceeds a critical threshold. This shock would resemble, in some ways, the shock that forms in front of Earth's magnetosphere when the supersonic solar wind encounters Earth's magnetic field. But comets lack intrinsic magnetic fields. The obstacle to the wind comes instead from the comet's ionized coma, a cloud of newly created ions that, through collisions and electromagnetic interactions, slows and deflects the incoming wind. Whether 3I/Atlas produces enough ions to generate a detectable shock remains uncertain. Observations will decide. The wind flows on, indifferent to human curiosity, indifferent to computational models, indifferent to the comet drifting through it. Protons and electrons stream past the comet at hundreds of kilometers per second, their paths barely deflected by the obstacle in their way. The vast majority of particles never interact with the comet at all. They pass by at distances of thousands or millions of kilometers, continuing their journey toward the heliopause and the interstellar medium beyond. Magnetic field lines drape around the ionized coma of 3I/Atlas like cloth settling over a stone. This draping occurs because the solar wind, carrying the sun's magnetic field frozen into its plasma, encounters an obstacle: the cloud of ions surrounding the comet's nucleus. The wind cannot penetrate the dense inner coma directly. Instead, it divides and flows around it, and the magnetic field lines, tied to the plasma through electromagnetic forces, follow the flow. The result is a characteristic pattern. Field lines pile up on the sunward side of the comet, stretch around the flanks, and extend far downstream in the anti-sunward direction, forming a magnetic tail that can reach lengths of several million kilometers. The draping process unfolds continuously as fresh ions are created through photoionization and charge exchange. Photoionization occurs when ultraviolet photons from the sun strike neutral molecules in the coma, stripping away electrons and creating ions. Charge exchange occurs when a solar wind proton collides with a neutral molecule, stealing an electron and becoming a neutral hydrogen atom while the molecule becomes ionized. Both processes add mass to the ionized component of the coma, which then picks up momentum from the solar wind through electromagnetic interactions. Only took missions to Comet Halley in 1986 to confirm this magnetic draping structure. The draped field lines carry electrical currents. These currents flow perpendicular to both the magnetic field and the pressure gradient in the plasma, forming current sheets that mark boundaries between regions of different field orientation. The currents themselves generate magnetic fields that modify the overall structure, creating a self-consistent configuration that balances magnetic pressure, plasma pressure, and the momentum flux of the incoming solar wind. No one can directly observe these field lines. They exist as mathematical constructs, lines of force that trace the direction a charged particle would spiral if placed in the field. Spacecraft equipped with magnetometers can measure the field's strength and direction at their location, providing point measurements that scientists integrate into global models. For 3I/Atlas, No spacecraft passes close enough to measure the field directly. The draping structure must be inferred from remote observations of the plasma tail, from theoretical models, and from analogies to other comets observed in situ. The magnetic tail of 3I/Atlas extends anti-sunward, carried by the solar wind flowing past the comet. Within this tail, the magnetic field strength diminishes with distance from the nucleus. At the inner boundary, near the coma's densest region, field strengths may reach tens of nanoteslas. At distances of millions of kilometers downstream, the field weakens to a few nanoteslas, approaching the background interplanetary field strength. The tail does not maintain a constant width. It expands gradually as it extends downstream, spreading out as the confined plasma diffuses into the surrounding solar wind. Plasma trapped within the magnetic tail moves at a different velocity than the surrounding solar wind. The tail plasma, originating from the comet itself, initially has nearly zero velocity in the comet's reference frame. As it interacts with the solar wind, it accelerates anti-sunward, but never quite matches the wind's speed. This velocity difference creates a shear layer at the boundary between tail plasma and wind plasma, a region where the velocity changes rapidly over short distances. Such layers are prone to instabilities, to the growth of waves and turbulent fluctuations that mix the two plasma populations. Only took decades of plasma physics research to understand how these instabilities develop. The structure of the magnetic tail responds to variations in the solar wind. When the wind density increases, the magnetic field drapes more tightly around the comet, compressing the tail and increasing field strengths near the nucleus. When the wind velocity increases, the tail stretches farther downstream, elongating the draped field lines. When the direction of the interplanetary magnetic field changes, the orientation of the draped field shifts correspondingly, tilting the tail in the plane perpendicular to the Sun-comet line. Disconnection events can occur in comet tails when the magnetic configuration becomes unstable. The stretched field lines downstream of the comet may reconnect with each other, snapping like overstretched rubber bands and severing the magnetic connection between the tail and the inner coma. The disconnected portion of the tail then drifts away, carried by the solar wind, while a new tail forms from freshly ionized material. These events were observed in multiple comets during the 20th century, photographed in visible light as the bright ionized tail suddenly detached and floated away from the comet's head. Whether 3I/Atlas will experience a disconnection event remains unknown. The likelihood depends on the comet's outgassing rate, on the variability of the solar wind, and on the geometry of the interplanetary magnetic field during the comet's passage through the inner solar system. If the comet passes through a region where the interplanetary field reverses direction, crossing the heliospheric current sheet, for instance, the chance of disconnection increases. But such crossings are difficult to predict far in advance. The magnetic field within the tail does not align perfectly with the tail axis. Detailed measurements from other comets reveal that the field often makes a small angle to the axis, creating a helical or twisted configuration. This twist may result from the rotation of the comet's nucleus, which imparts a small tangential velocity component to the outflowing ions, or from the draping of a pre-existing twist in the interplanetary field. The exact cause remains debated, and observations of 3I/Atlas may provide new constraints on these theories. Timescales in the interaction span many orders of magnitude. The solar wind flows past the comet in a matter of hours, the time it takes for plasma moving at 400 kilometers per second to cross a distance of several million kilometers. But the structure of the draped magnetic field evolves more slowly, adjusting over days as the comet's outgassing rate changes and as the solar wind conditions vary. The comet's nucleus rotates on a time scale of hours, creating periodic variations in outgassing that propagate through the coma and eventually affect the tail structure. The solar wind itself carries fluctuations on timescales ranging from seconds to weeks. Reflecting the turbulent nature of the flow and the variability of conditions at the Sun's surface, only took careful timing measurements to disentangle these overlapping timescales. The energy density in the magnetic field near 3I/Atlas is small compared to the kinetic energy density of the solar wind. Magnetic pressure contributes only a minor fraction of the total pressure balance in most regions of the interaction. But in certain locations, particularly in the draped field region close to the nucleus, the magnetic pressure can become significant, strong enough to affect the flow of plasma and to create localized structures that would not exist in a purely hydrodynamic interaction. Ions, freshly created in the outer coma, undergo a process called pickup. Initially, these ions have nearly zero velocity in the frame of the comet, but they possess electrical charge, and they find themselves immersed in the magnetic field carried by the solar wind. The electromagnetic forces exerted by the moving wind act on these stationary ions, accelerating them up to the wind's velocity over a distance of a few hundred to a few thousand kilometers. During this acceleration, the ions gain energy extracted from the bulk motion of the wind, causing the wind to slow slightly. The slowdown is barely perceptible on a per-particle basis, but becomes significant when integrated over the vast number of ions picked up from the coma. The picked-up ions do not move in straight lines. The magnetic field forces them into helical trajectories, spiraling around the field lines as they flow downstream. These spirals are typically much larger than the spirals traced by solar wind protons because the picked-up ions start with higher velocities perpendicular to the field. The resulting distribution of ion velocities becomes highly anisotropic, with different speeds in directions parallel and perpendicular to the magnetic field. This anisotropy can drive plasma instabilities, generating waves that scatter the ions and eventually isotropize their velocity distribution. Only took in situ measurements at Comet Giacobini-Zinner to observe pickup ions directly. The draped magnetic field around 3I/Atlas exists in a state of frozen time. The field lines stretch from the Sun through millions of kilometers of space, threading through the comet's coma and extending downstream into the distant solar wind. Each field line carries a history, a record of the conditions at the Sun when the plasma now threading through the comet was launched from the corona days earlier. The comet samples this history passively, its ionized tail-tracing field lines that encode information about solar activity from the recent past. The heliosphere resembles a bubble blown by the Sun into the interstellar medium. This bubble extends far beyond the orbits of the planets, far beyond the Kuiper belt, where dwarf planets and cometary nuclei drift in the cold outer reaches of the solar system. The boundary of the heliosphere, the heliopause, lies at a distance of approximately 120 to 130 astronomical units from the Sun, in the direction toward which the solar system moves through the galaxy, and farther in other directions. At this boundary, the pressure of the solar wind balances the pressure of the interstellar plasma and the magnetic field pervading the local interstellar medium. Only took Voyager 141 years of travel to cross the heliopause in 2012. The shape of the heliosphere is not spherical. The solar system moves through the local interstellar medium at a velocity of roughly 26 kilometers per second, creating a preferential direction. In the direction of motion, the nose of the heliosphere, the heliopause lies closer to the Sun because the ram pressure of the interstellar medium compresses the heliosphere. In the opposite direction, the tail of the heliosphere, the boundary extends much farther, stretched into a long tail by the solar wind flowing outward and by the wake created by the solar system's motion. Through the interstellar medium, the region just inside the heliopause, called the heliosheath, contains solar wind plasma that has been slowed and heated as it approaches the boundary. The termination shock marks the inner edge of the heliosheath, located at approximately 90 to 100 astronomical units depending on direction. At this shock, the solar wind transitions from supersonic to subsonic flow. Before the shock, the wind travels faster than the speed of sound in the plasma. After the shock, it moves more slowly, its kinetic energy partially converted to thermal energy and to energy in accelerated particles. The interstellar medium beyond the heliopause consists of partially ionized hydrogen and helium, with trace amounts of heavier elements. The density of this medium is approximately 0.1 particles per cubic centimeter, far denser than the solar wind in the outer heliosphere, but still an excellent vacuum by terrestrial standards. The temperature of the interstellar plasma is approximately 6,000 Kelvin, comparable to the temperature of the Sun's visible surface. The magnetic field in the local interstellar medium has a strength of roughly 3 microgauss, or 0.3 nanoteslas, oriented approximately perpendicular to the direction of the solar system's motion. Only took data from both Voyager spacecraft to constrain these interstellar medium properties. The heliopause itself is not a sharp boundary. Rather, it is a transition region spanning perhaps 1 to 2 astronomical units in thickness, within which the properties of the plasma change gradually from solar wind dominated to interstellar medium dominated. Both Voyager 1 and Voyager 2 measured multiple crossings or fluctuations near the heliopause, suggesting that the boundary moves back and forth in response to variations in solar wind pressure and changes in interstellar medium conditions. No one knows the precise three-dimensional shape of the heliopause. Models suggest it may resemble a bullet shape, with a rounded nose facing the direction of the solar system's motion and a long tail extending behind. But the models disagree on details. Some predict a relatively smooth surface. Others suggest instabilities and turbulence create ripples and folds in the boundary. The models also disagree on whether a bow shock forms ahead of the heliopause, where the interstellar medium first encounters the obstacle presented by the solar system's passage. Voyager 1 did not detect such a bow shock, suggesting either that it does not exist or that the spacecraft passed through it without recognizing the signatures. The heliosphere shields the inner solar system from most galactic cosmic rays, high-energy particles accelerated in supernova remnants, and other violent astrophysical environments. These particles carry energies far exceeding those of solar wind particles, and they arrive at the heliosphere from all directions. The magnetic field in the heliosheath, turbulent and tangled, scatters many of these cosmic rays, preventing them from reaching the inner planets. The efficiency of this shielding varies with the solar cycle. During solar maximum, when the solar wind is more turbulent and the heliospheric magnetic field is more disordered, cosmic ray fluxes in the inner heliosphere decrease. During solar minimum, when the wind is calmer, cosmic rays penetrate more easily. Only took 6 decades of cosmic ray observations to map this solar modulation effect. The heliosphere evolves over time as the sun's activity waxes and wanes. During periods of high solar activity, the solar wind carries more momentum, pushing the termination shock and heliopause farther from the sun. During periods of low activity, the pressure weakens and the boundaries retreat inward. These changes unfold over years to decades, reflecting the 11-year solar cycle and longer-term variations in the sun's magnetic field. Voyager 2 crossed the heliopause at a closer distance than Voyager 1, partly because it followed a different trajectory and partly because it reached the boundary during a different phase of the solar cycle. The temperature structure of the heliosheath surprised researchers when the Voyager spacecraft first entered it. Models had predicted that the solar wind would cool significantly after crossing the termination shock, its kinetic energy converted to thermal energy. Instead, the measured temperatures exceeded predictions by factors of several. The discrepancy suggests that additional heating mechanisms operate in the heliosheath, perhaps waves, perhaps magnetic reconnection, perhaps energy injection from the turbulent boundary layer at the heliopause. Between the orbits of the planets and the distant heliopause, the solar wind undergoes a long, slow evolution. At Earth's orbit, the wind consists of discrete streams, fast wind from coronal holes, slow wind from other regions that interact and create structure in the flow. At Jupiter's orbit, some of this structure persists, but interactions between streams have smoothed out many of the sharp boundaries. At Neptune's orbit, the wind has become more uniform. Its velocity and density variations averaged out over the long transit time from the Sun. By the time the wind reaches the termination shock, it has lost most memory of short-term variations at the Sun, retaining only the long-term average properties. Only took 4 spacecraft in the outer solar system to trace this evolution. 3 I/Atlas moves through the inner heliosphere, far from the heliopause, far from the termination shock. At 5 astronomical units, the comet resides deep within the region where the solar wind retains its supersonic velocity and its stream structure. The boundary of the Sun's influence lies more than 100 astronomical units away, a distance the comet will never reach, given its hyperbolic trajectory. The comet will pass perihelion, swing around the Sun, and begin its outward journey while still well within the heliosphere, eventually exiting into interstellar space after millions of years of travel. The heliosphere contains structures on all scales. The largest structure is the bubble itself, spanning hundreds of astronomical units. Within the bubble, smaller structures include the heliospheric current sheet, stream-stream interaction regions, and the magnetic sectors that divide the heliosphere into regions of opposite polarity. At still smaller scales, turbulence creates fluctuations in the magnetic field and plasma properties on scales ranging from astronomical units down to hundreds of kilometers. And at the smallest scales, kinetic processes, interactions between individual particles and the electromagnetic fields, shape the plasma behavior in ways that continuum models cannot capture. The heliosphere is not isolated from the galaxy. The interstellar medium through which the solar system moves is not uniform, over time scales of millions of years. The Sun passes through regions of varying density, temperature, and magnetic field strength. When the Sun enters a denser cloud, the ram pressure on the heliopause increases, compressing the heliosphere. When the Sun exits into a less dense region, the heliosphere expands. These variations may have influenced Earth's climate in the past by modulating the cosmic ray flux reaching Earth's atmosphere. Though the strength of this effect remains debated, only took geological records and cosmic ray transport models to suggest this possible connection. The heliosphere will exist as long as the Sun continues to produce solar wind, likely for billions of years into the future. But its properties will change as the Sun evolves. In approximately 5 billion years, when the Sun exhausts the hydrogen fuel in its core and begins fusing helium, it will expand into a red giant. The solar wind during this phase will be much denser and slower, and the heliosphere will adopt a different configuration. Eventually, the Sun will shed its outer layers entirely, leaving behind a white dwarf surrounded by a planetary nebula. The white dwarf will produce no solar wind, and the heliosphere will disappear. Coronal holes appear as dark regions in ultraviolet and X-ray images of the Sun. These holes are not voids, but rather regions where the corona is cooler and less dense than the surrounding material. The darkness arises because cooler plasma emits less radiation at ultraviolet and X-ray wavelengths, making these regions appear dim in images captured by solar observatories. Coronal holes form where the Sun's magnetic field lines extend directly outward into space rather than looping back to the surface, creating open magnetic field configurations that allow plasma to escape more easily. The fast solar wind originates in coronal holes. Plasma streaming along open field lines accelerates to velocities exceeding 700 kilometers per second by the time it reaches several solar radii from the Sun's surface. The acceleration mechanism remains incompletely understood. Early models suggested that thermal pressure gradients drive the acceleration, with the high temperature of the corona providing sufficient energy to push particles to escape velocity. But detailed measurements reveal that the corona is not hot enough to explain the observed wind speeds through thermal pressure alone. Additional forces must contribute. Only took high-resolution spectroscopy to reveal this energy shortfall. Wave heating offers one possible mechanism. Magnetic waves generated in the sun's convection zone propagate upward into the corona, carrying energy that can be deposited in the plasma through various dissipation processes. Alfvén waves, magnetic oscillations named after Hannes Alfvén, who predicted their existence in 1942, travel along magnetic field lines and can accelerate particles preferentially in the direction parallel to the field. Observations from Parker's solar probe show strong Alfvén wave activity in the corona, consistent with this mechanism. Though the detailed coupling between waves and particles remains an active area of research. Coronal holes evolve on timescales ranging from days to months. Small holes may appear and disappear within a week or two. Large polar coronal holes, which form near the sun's north and south poles, can persist for years, expanding and contracting as the solar cycle progresses. During solar minimum, the sun's magnetic field adopts a relatively simple dipole configuration, with large coronal holes covering both polar regions. During solar maximum, the magnetic field becomes more complex, and coronal holes can appear at any latitude, sometimes fragmenting into multiple smaller holes. The sun rotates with a period of approximately 27 days at its equator, slower at higher latitudes due to differential rotation. As the sun rotates, coronal holes sweep past Earth's orbital plane, and the fast wind streams originating from these holes arrive at Earth in a periodic pattern. When Earth sits within a fast wind stream, geomagnetic activity increases. Auroras become more frequent. The outer layers of Earth's atmosphere heat and expand, increasing drag on satellites in low Earth orbit. These effects recur approximately every 27 days when the same coronal hole rotates back into alignment with Earth. Only took decades of space weather observations to recognize this 27-day recurrence pattern. At the distance of 3 I/Atlas, approximately 5 astronomical units from the Sun. The difference between fast and slow wind has diminished somewhat but remains detectable. Fast wind streams, launched from coronal holes at high speed, maintain much of their velocity during the journey outward. Slow wind streams, originating from other regions of the corona, travel more slowly and are often compressed by faster streams overtaking them from behind. The compression creates correlating interaction regions, zones of enhanced density and magnetic field strength that spiral outward through the heliosphere, following the Parker spiral geometry. The comet samples this structured flow as it moves through the inner heliosphere. Sometimes it finds itself immersed in fast wind, its coma buffeted by a high-velocity stream of particles. At other times, slow wind surrounds it, or the comet crosses the boundary between fast and slow streams, experiencing rapid changes in wind speed and density over the course of a few hours. These variations modulate the rate of ion production in the coma and the structure of the magnetic field draping around the comet. Coronal holes emit plasma with a distinctive chemical composition. Fast wind from coronal holes contains a higher ratio of alpha particles, helium nuclei to protons compared to slow wind. The charge states of heavier ions also differ between the two wind types. Fast wind shows lower charge states on average, indicating that the plasma originates from cooler or less dense regions of the corona where fewer electrons have been stripped from the ions. These compositional differences serve as tracers, allowing scientists to identify the source regions of different wind streams even after the plasma has traveled millions of kilometers from the sun. Only took mass spectrometers on spacecraft to measure these subtle compositional differences. The edges of coronal holes are regions of particular interest. Here, open field lines that extend into space lie adjacent to closed field lines that loop back to the solar surface. The boundary between these two magnetic topologies is not sharp, but rather a transition zone where field lines may shift between open and closed configurations through magnetic reconnection. This reconnection releases energy, heats plasma, and may contribute to the acceleration of the slow wind that flows along the edges of coronal holes. No complete model of coronal hole structure exists. Observations provide snapshots of the holes as they appear at a given moment, but the three-dimensional magnetic field configuration within and around the holes remains difficult to measure. Models extrapolate the observed surface magnetic field into the corona using mathematical techniques that assume the corona is current-free or nearly so. These extrapolations predict the locations of open field lines and the shapes of coronal holes, but the predictions sometimes disagree with observations, suggesting that currents in the corona play a more important role than the models assume. The temperature within coronal holes is not uniform. Near the base of the corona, just above the sun's visible surface, temperatures in coronal holes may be lower than in other coronal regions, perhaps 1 million Kelvin compared to 2 or 3 million Kelvin elsewhere, but farther out. Along the open field lines extending into space, the temperature profile changes. Fast wind plasma cools as it expands outward, but the cooling rate depends on whether energy continues to be deposited into the plasma through wave heating or other mechanisms. Measurements from multiple spacecraft at different distances from the Sun help constrain these temperature profiles. Only took coordinated observations from missions at varying heliocentric distances to map the temperature evolution. Coronal holes rotate with the Sun, but they are not rigidly attached to the solar surface. The holes can drift in longitude and latitude, expanding into some regions and retreating from others as the underlying magnetic field evolves. This evolution is driven by the continuous emergence of new magnetic flux from below the surface and by the transport of magnetic flux across the surface through convective flows and differential rotation over months to years. The pattern of coronal holes can change dramatically, reflecting the Sun's magnetic activity cycle. The interaction between fast and slow wind creates turbulence throughout the heliosphere, where fast streams overtake slow streams. Velocity shears develop. These shears are unstable, breaking down into turbulent fluctuations that transfer energy across a range of scales. The turbulence affects the propagation of energetic particles through the heliosphere, scattering them and reducing their ability to penetrate to the inner solar system. It also affects the transport of magnetic flux and the connectivity between different regions of the heliosphere. 3. I/Atlas crosses through regions of the heliosphere dominated by fast wind and regions dominated by slow wind. The comet has no way to distinguish between them except through the local effects they produce. When fast wind arrives, the comet's tail may brighten and elongate as the higher ram pressure compresses the magnetic field and accelerates ions more efficiently. When slow wind surrounds the comet, the tail may weaken slightly, its structure responding to the gentler flow. These variations create a flickering quality in the comet's appearance, a subtle modulation visible to observers with sensitive instruments. Only took one interstellar comet to trace the Sun's breadth at 5 astronomical units. The plasma tail of 3 I/Atlas glows in wavelengths invisible to the human eye, carbon monoxide ions, stripped of an electron through photoionization or charge exchange, emit photons at ultraviolet wavelengths when electrons recombine with the ions or when the ions are excited by collisions with solar wind particles. This emission concentrates in specific spectral lines, narrow ranges of wavelength determined by the quantum mechanical structure of the carbon monoxide molecular ion. Observatories equipped with ultraviolet sensitive detectors capture these photons, building images of the tail that reveal its length, width, and brightness variations. The tail does not glow uniformly. Brightness fluctuations appear along its length. created by variations in the ion production rate in the coma and by structures in the solar wind, density enhancements, velocity changes, magnetic field rotations. These structures sweep past the comet and leave imprints in the tail as they drag ionized material downstream. A patient observer watching the tail over hours or days sees waves of brightness propagate anti-sunward. Each wave, marking the passage of a solar wind, feature through the comet's interaction region. Only took time-resolved imaging to reveal these propagating structures. The tail's color, if observed in visible light, appears bluish-green. The blue component arises from emission by ionized carbon monoxide. The green component comes from neutral carbon molecules in the coma, which fluoresce in green wavelengths when excited by sunlight. The combination creates a distinctive hue that helps astronomers distinguish plasma tails from dust tails, which appear yellow-white because they simply reflect sunlight without adding emission from fluorescing molecules. Dust tails and plasma tails follow different trajectories. Dust tails curve gently. Their shape determined by the balance between solar gravity, pulling the dust grains inward, and solar radiation pressure pushing them outward. Plasma tails point almost directly away from the sun, shaped by the solar wind and magnetic field rather than by radiation pressure. The two tails often appear side by side in wide-field images of comets, creating a forked appearance. For 3I/Atlas, the dust tail remains faint. The comet produces relatively little dust compared to some other comets, making the plasma tail the more prominent feature. The plasma tail extends farther than any physical structure connected to the comet. The ions composing the tail have been stripped from the coma and swept away by the solar wind. They no longer orbit the comet's nucleus. They do not follow the comet's trajectory. Instead, they stream anti-sunward at velocities approaching the solar wind speed, gradually mixing with the surrounding plasma and becoming indistinguishable from the background. The tail persists only because the comet continuously produces new ions to replace those carried away, maintaining a steady-state structure that appears fixed relative to the comet but actually consists of constantly refreshed material. Only took careful velocity measurements to confirm that tail plasma flows outward, not with the comet. The brightness of the tail depends on multiple factors. Increased solar ultraviolet flux enhances the photoionization rate, creating more ions and therefore more emission. Increased solar wind density provides more electrons and protons to excite the ions, also increasing emission. Changes in the comet's outgassing rate directly affect how many neutral molecules are available to be ionized. These factors vary independently, creating complex brightness patterns that reflect both solar activity and the comet's intrinsic behavior. Spectroscopy of the tail reveals the presence of multiple molecular species. Carbon monoxide ions dominate, but water group ions, fragments of water molecules broken apart by ultraviolet radiation and electron impacts, also contribute. These include H2O+, OH+, and O+. Nitrogen-bearing molecules may appear as well, such as Cn+ and N2+, though these are typically less abundant. The relative strengths of emission lines from different species provide clues about the composition of the nucleus and the processes occurring in the coma. Polarization measurements add another layer of information. Scattered sunlight from dust grains exhibits polarization. The electric field of the light waves oscillates preferentially in certain directions. The degree of polarization depends on the size, shape, and composition of the grains. Plasma emission, in contrast, shows little polarization unless the emission process involves anisotropic distributions of electrons or magnetic fields. By measuring polarization across the comet's coma and tail, observers can separate dust-scattered light from plasma emission and map the spatial distribution of each component. Only took decades of comet observations to refine these polarimetric techniques. The tail writes in plasma. Its structure encodes information about the magnetic field threading through it, about the velocity of the solar wind, about the density and temperature of the surrounding space. This information exists in three-dimensional space, but observers on Earth see only a two-dimensional projection, the tail as it appears from our particular viewing angle. The true three-dimensional structure must be inferred using models that account for the projection effects and the physics of the plasma-magnetic field interaction. Rays sometimes appear in comet tails, narrow, bright structures that extend radially away from the nucleus. These rays may trace magnetic field lines or plasma flow streamlines, though their exact origin remains debated. They appear and disappear on timescales of hours, suggesting they result from transient features in the solar wind or from instabilities in the comet-wind interaction. High-resolution images capture these rays in exquisite detail, revealing fine structure that challenges models to reproduce. The tail of 3 I/Atlas displays no anomalies that would mark it as foreign. Interstellar comets might be expected to exhibit unusual compositions or behaviors, carrying chemical signatures from their formation in a different stellar environment. But the spectra obtained so far show familiar molecular species in expected ratios. The tail behaves as tails do. The interaction with the solar wind follows known physics. If not for the comet's hyperbolic trajectory, the unambiguous orbital signature of an interstellar origin, one might mistake 3 I/Atlas for a member of the Sun's own comet family. Only took precise astrometry to reveal the hyperbolic orbit. The magnetic field within the tail varies in strength and direction, near the nucleus, where the draped field lines converge and compress. Field strengths may reach tens of nanoteslas. Farther downstream, the field weakens and the geometry becomes more irregular as the tail plasma mixes with the solar wind. Turbulence develops at the tail's boundaries, where velocity and density gradients drive instabilities. These instabilities generate waves that propagate through the plasma, carrying energy and momentum, redistributing magnetic flux. Ions in the tail experience forces from the magnetic field, from the electric field associated with the plasma flow, and from collisions with other particles. The relative importance of these forces depends on the ion's mass, charge, and velocity. Light ions like protons respond quickly to electromagnetic forces, gyrating around field lines with small radii. Heavier ions like carbon monoxide ions gyrate more slowly, with larger radii, and are less tightly bound to the field lines. This difference in behavior creates charge separation and drives electrical currents that help maintain the plasma's quasi-neutrality. No ion in the tail remembers its origin. The molecules that evaporated from the nucleus hours or days ago, that were ionized in the coma, that were picked up by the solar wind and accelerated downstream. These molecules have been transformed. They have collided with electrons, exchanged charge with neutral atoms, emitted photons, and absorbed energy from electromagnetic fields. The tail plasma is a product of continuous processing, a flowing archive of interactions that have erased the specific histories of individual particles while preserving statistical properties that reflect the overall environment. The tail persists in darkness beyond the range of human vision. Ultraviolet photons from the tail travel through space at light speed, reaching Earth's orbit 8 minutes after they are emitted if the comet happens to be 1 astronomical unit away, longer if the distance is greater. These photons carry information encoded in their wavelengths, their arrival times, their polarization states. Telescopes gather them, spectrometers disperse them, detectors count them, and computers transform them into images and spectra that scientists analyze in search of understanding. Only took centuries of optical development to build instruments sensitive enough to detect cometary plasma emission. The tail of 3 I/Atlas will fade as the comet recedes from the sun. Decreased solar heating will reduce the outgassing rate. Fewer neutral molecules in the coma will mean fewer ions in the tail. The plasma emission will weaken, first becoming difficult to detect, then vanishing entirely as the comet crosses beyond the distance where solar radiation is too feeble to maintain significant ionization, the tail will disappear, not suddenly, but gradually, dimming over weeks and months until it merges with the darkness of space and only the faint reflected light from the nucleus remains visible to the most powerful telescopes. Between the violent eruptions of coronal mass ejections, the solar wind enters periods of unusual quiet. These calm intervals can last days or weeks, during which the wind's velocity, density, and magnetic field strength vary only gently. The turbulent fluctuations that normally characterize the wind diminish. The flow becomes nearly laminar, parallel streamlines, minimal mixing, a steady state that persists until the next disruption arrives. Scientists call these periods ambient solar wind conditions, though ambient understates the rarity of such sustained tranquility in a system normally dominated by variability. The calm arises from a particular configuration of the Sun's magnetic field and corona. When no active regions are producing flares, when no coronal holes are positioned to send fast wind streams toward a particular location in space, when the heliospheric current sheet lies relatively flat and stable, the solar wind at that location can achieve a nearly constant state. The proton density might hover around 5 particles per cubic centimeter. The velocity might hold near 400 kilometers per second. The magnetic field might maintain a strength of 6 nanoteslas and a direction that changes only slowly over hours. Only took continuous spacecraft monitoring to recognize how rare these calm intervals are. 3I/Atlas drifts through such a calm now. In late 2024, as solar activity approaches the minimum phase of the current cycle, the Sun's surface displays few sunspots. The corona exhibits a simple structure with large polar coronal holes and minimal complexity at lower latitudes. The wind reaching the comet's location has traveled from a quiet region of the corona, launched days earlier when conditions were even more stable than now. The comet's plasma tail responds to this steadiness, maintaining a relatively constant brightness and length. Its structure smooth and unperturbed by the shocks and discontinuities that often ripple through the heliosphere. But the calm will not last. Solar activity follows an 11-year cycle, and the current minimum is ending. Observers note increasing numbers of small sunspots appearing at mid-latitudes on the Sun's surface. These spots mark the emergence of new magnetic flux from the Sun's interior. Flux that will eventually rise into the corona and create active regions capable of producing flares and coronal mass ejections. Within months, the Sun's behavior will shift. The frequency of eruptions will increase. The solar wind will become more variable. The heliosphere will enter a more turbulent phase. The transition from solar minimum to solar maximum unfolds gradually. The first eruptions of the new cycle are typically small and infrequent. As the cycle progresses, the eruptions grow larger and more common. By the time solar maximum arrives, roughly 5 to 6 years after minimum, the Sun may produce multiple coronal mass ejections per day. Some of these ejections carry enormous quantities of plasma, exceeding 10 billion tons. Launched into space at speeds of several thousand kilometers per second. Such eruptions create interplanetary shocks that propagate through the heliosphere, disrupting the ambient wind and affecting any comets, planets, or spacecraft in their paths. Only took observations over multiple solar cycles to characterize this variability. The solar wind speed during calm periods depends primarily on the source region from which the wind originates. Wind from the edges of coronal holes typically flows at intermediate speeds, 500 to 600 kilometers per second. Wind from quiet equatorial regions flows more slowly, at 300 to 400 kilometers per second. Wind from the interiors of large coronal holes flows fastest, at 700 to 800 kilometers per second. At any given moment, different parts of the heliosphere receive wind from different source regions, creating a patchwork of velocities that rotates with the Sun. The magnetic field during calm periods often adopts a relatively smooth configuration. The Parker spiral geometry dominates, with field lines wrapping around the Sun in a regular pattern. The heliospheric current sheet may oscillate above and below the solar equator with a modest amplitude, creating a gentle warping rather than the extreme corrugations seen during solar maximum. Crossings of the current sheet occur regularly, approximately once per solar rotation, as the sheet's wave pattern sweeps past observers in the inner heliosphere. Temperature measurements during calm periods reveal subtle structure in the solar wind. Proton temperatures typically range from 10,000 to 100,000 Kelvin at 1 astronomical unit. Depending on wind speed and other factors, electron temperatures are often different from proton temperatures, sometimes higher, sometimes lower, because collisions between particles are too infrequent to establish thermal equilibrium. The solar wind is a collisionless plasma over most length scales, meaning that particles interact primarily through long-range electromagnetic forces rather than through direct contact. Only took detailed plasma measurements to reveal the non-equilibrium nature of the wind during calm periods. The solar wind's properties at different locations in the heliosphere become predictable. Models can extrapolate conditions observed at one spacecraft to predict conditions that will arrive at another spacecraft days later, accounting for the transit time and the evolution of the wind during its journey. This predictability enables space weather forecasting, allowing operators of satellites and power grids to prepare for the arrival of solar wind structures that might affect their systems. But the predictability holds only during calm periods. When coronal mass ejections and other transient events disrupt the flow, predictions become much less reliable. The calm provides an opportunity to study the solar wind's fine structure. Small-scale fluctuations, waves, and instabilities that would be overwhelmed by large-scale variability during active periods become detectable during calm intervals. Researchers analyze these fluctuations to understand the microphysics of the plasma, the processes that heat particles, that generate waves, that scatter energetic particles. The fluctuations span a wide range of frequencies, from millihertz oscillations with periods of many minutes to kilohertz oscillations with periods of milliseconds. The wind during calm periods carries information about the Sun's interior. The elemental composition of the wind reflects the composition of the solar atmosphere, which in turn reflects the composition of the Sun's convective zone, the outer 30% of the Sun's radius where energy is transported by convective motions rather than by radiation. Measurements of isotopic ratios in the wind provide constraints on models of solar formation and evolution. The ratios of helium to hydrogen, of carbon to oxygen, of neon to magnesium all carry clues about the history of the material from which the Sun formed. Only took decades of compositional measurements to build a detailed picture of solar abundances. 3 I/Atlas experiences the calm as a gentle, constant pressure. The solar wind particles strike the comet's coma at a steady rate, ionizing molecules and carrying them away in the plasma tail. The magnetic field drapes smoothly around the coma, its configuration stable over hours to days. No shocks arrive to compress the field and brighten the tail. No discontinuities pass by to twist the field lines and create kinks in the tail structure. The comet drifts through the heliosphere in a state of relative equilibrium, its interaction with the solar wind proceeding at a pace set by the slow evolution of the comet's outgassing and the gradual changes in the ambient wind. But instruments monitoring the Sun detect the first signs of change. A small sunspot group appears at 30 degrees latitude in the Sun's northern hemisphere. The group contains several spots, their dark cores surrounded by brighter regions called penumbrae. The magnetic field in the sunspot group measures several thousand Gauss, about 10,000 times stronger than the interplanetary magnetic field. This strong field inhibits convective motions, preventing hot plasma from rising to the surface and causing the sunspot to appear dark compared to its surroundings. The sunspot group is young, just 2 days old, still growing as magnetic flux continues to emerge from below the surface. Over the coming days, it may evolve into an active region capable of producing flares, or it may fragment and disperse, its magnetic flux spreading across the solar surface and eventually being transported into the corona. Either way, its presence signals the end of the current calm period. The sun stirs. Activity rises. The wind's tranquility will give way to gusts. Only took the appearance of one sunspot group to herald the coming change. Magnetic reconnection occurs when oppositely directed magnetic field lines approach each other, break, and rejoin in a new configuration. This process converts magnetic energy stored in the stressed field into kinetic energy of particles and heat. Reconnection happens throughout the heliosphere, in the solar corona, at the boundaries of coronal holes, in the heliospheric current sheet, and in the magnetic tails of comets. The process unfolds rapidly, typically on time scales of seconds to minutes, releasing energy that has accumulated gradually over much longer periods. The physics of reconnection involves the breakdown of flux freezing. Under normal circumstances, magnetic field lines are frozen into the plasma, meaning that plasma and field move together and cannot slip past each other. But in thin regions where the magnetic field changes direction rapidly, called current sheets, the idealized assumption of perfect flux freezing fails. Particles can cross field lines, allowing the topology of the field to change. The current sheet acts as a site where the magnetic field can reconfigure itself, releasing the energy stored in the field's stress geometry. Only took decades of theoretical work and spacecraft observations to understand reconnection physics. The rate of reconnection depends on several factors. The strength of the magnetic field on either side of the current sheet matters. Stronger fields store more energy and can drive faster reconnection. The density and temperature of the plasma matter, higher density, provides more particles to carry current, while higher temperature increases particle velocities and allows faster dissipation of energy. The thickness of the current sheet matters. Thinner sheets concentrate the magnetic field gradient more sharply, enhancing the rate at which field lines can break and rejoin. Reconnection in the solar corona produces solar flares. When the coronal magnetic field becomes twisted and stressed by motions of the solar surface, energy accumulates in the field. Eventually, the stress becomes too great, and reconnection begins at a site where oppositely directed field lines come close together. The reconnection releases energy explosively, heating plasma to tens of millions of Kelvin and accelerating particles to a significant fraction of the speed of light. The heated plasma emits X-rays and extreme ultraviolet radiation. The accelerated particles stream along newly reconnected field lines, sometimes reaching the solar surface and causing radio bursts. Coronal mass ejections often accompany flares. Though the two phenomena are distinct, reconnection low in the corona can open previously closed field lines, allowing a large volume of plasma to escape into space. This escaping plasma forms the coronal mass ejection, a billion-ton cloud that propagates through the heliosphere at speeds ranging from a few hundred to a few thousand kilometers per second. The ejection carries with it a twisted magnetic field structure, often in the form of a magnetic flux rope, a bundle of field lines that wrap helically around a central axis. Only took coronagraph observations from space to reveal the full structure of coronal mass ejections. Reconnection in interplanetary space occurs in the heliospheric current sheet and at the boundaries between different solar wind streams, when the current sheet oscillates above and below the solar equator. Spacecraft crossing the sheet measure abrupt reversals in the magnetic field direction. These reversals mark locations where field lines of opposite polarity come close together. Reconnection at these sites can locally heat the plasma, accelerate particles, and create small-scale structures in the field that propagate away from the reconnection site. The rate of reconnection in interplanetary space is typically much slower than in the solar corona. The plasma density is lower by many orders of magnitude, and the magnetic field is weaker. These factors reduce the efficiency of energy release. Nevertheless, reconnection still occurs, and its signatures can be detected by spacecraft equipped with particle detectors and magnetometers. Sudden changes in field direction, brief enhancements in electron temperature, and the appearance of energetic particles all indicate that reconnection has occurred nearby. Reconnection in comet magnetotails happens when the stretched field lines downstream of the comet become unstable. The tail's magnetic field carries a current flowing across the tail, separating regions of opposite polarity. This current sheet can become thin and pinched, creating conditions favorable for reconnection. When reconnection occurs, the tail beyond the reconnection site disconnects from the inner coma and drifts away. Carried by the solar wind, a new tail then forms from fresh ions produced in the coma. This disconnection event can repeat multiple times during a comet's passage through the inner solar system. Only took ground-based observations of Comet Halley to capture a disconnection event on camera. The geometry of reconnection varies depending on the local conditions. In some cases, reconnection occurs at a single localized site, a point in two-dimensional models or a line in three-dimensional space where field lines of opposite polarity meet. In other cases, reconnection occurs over an extended region, with multiple reconnection sites active simultaneously. The resulting magnetic configuration can be complex, with magnetic islands and flux ropes forming in the reconnection region and propagating away as coherent structures. Reconnection does not occur in isolation. The energy released heats the plasma, which can drive waves and instabilities. These waves propagate away from the reconnection site, carrying energy and momentum. The waves can interact with particles, scattering them and changing their velocities. This wave-particle interaction represents a second stage of energy conversion, transforming the bulk kinetic energy of the plasma into random thermal motion of individual particles. The particles accelerated during reconnection can achieve very high energies. In solar flares, electrons and protons are accelerated to energies of millions of electron volts, creating populations of energetic particles that stream through the heliosphere. These particles can reach Earth within minutes to hours, causing sudden increases in radiation levels detected by spacecraft and ground-based instruments. The acceleration mechanism is not fully understood. Multiple processes likely contribute, including direct acceleration by electric fields in the reconnection region and stochastic acceleration by waves and turbulence downstream of the reconnection site. Only took decades of particle observations during flares to constrain acceleration models. Magnetic reconnection represents one of the fundamental processes by which energy stored in magnetic fields is released in astrophysical plasmas. The process operates not only in the solar system, but also in stellar coronae, in magnetospheres of planets throughout the galaxy, in accretion disks around black holes, and in the interstellar medium. The basic physics remains the same. Oppositely directed magnetic field lines break and rejoin, converting magnetic energy into other forms. But the conditions vary enormously, from the high densities and strong fields of stellar coronae to the low densities and weak fields of intergalactic space. 3I/Atlas may experience reconnection in its magnetic tail if conditions become favorable. The comet's interaction with the solar wind creates a current sheet in the tail where field lines of opposite polarity come close together. If the solar wind becomes turbulent, or if a coronal mass ejection passes by, the stress on the tail's magnetic field may increase, triggering reconnection. The disconnected portion of the tail would then drift away, visible for a time as a detached blob of glowing plasma before dispersing into the background solar wind. Whether such an event will occur remains uncertain. The conditions must align. The comet must be producing enough ions to create a substantial tail. The solar wind must provide sufficient disturbance, and the magnetic geometry must favor reconnection. These conditions may or may not be met during 3E/Atlas's passage through the inner solar system. Observers watch and wait, ready to capture the event if it happens. Content to analyze other aspects of the comet's behavior if it does not, only took patience and continuous monitoring to catch rare events when they occur. The Sun's magnetic field reverses polarity approximately every 11 years. During this reversal, the field transitions from a configuration where the north magnetic pole has one polarity to a configuration where it has the opposite polarity. The reversal does not happen instantaneously. Instead, it unfolds over months as the magnetic field at the poles weakens, disappears, and re-emerges with reversed polarity. During this transition, the Sun's overall magnetic geometry becomes complex and chaotic, with multiple regions of positive and negative polarity scattered across the surface. The 11-year cycle is actually half of a 22-year magnetic cycle. After the first 11 years, the Sun's field has reversed once. After another 11 years, it reverses again, returning to its original polarity. This 22-year period represents the true cycle of the Sun's magnetic field. Though solar activity, sunspots, flares, coronal mass ejections follows the 11-year pattern because activity depends on field strength rather than polarity. Only took centuries of sunspot records to reveal the 11-year cycle. Solar minimum occurs when the Sun's magnetic field is strongest at the poles and weakest elsewhere. Sunspot counts drop to near zero. The corona adopts a simple structure with large coronal holes at the poles and a relatively quiet equatorial region. The solar wind at this time consists primarily of slow wind from the equator and fast wind from the polar holes. The heliospheric current sheet, which marks the boundary between regions of opposite magnetic polarity, lies close to the solar equatorial plane, with only modest warping above and below the equator. Solar maximum occurs when the Sun's magnetic field is most complex. Sunspots appear at many latitudes. Active regions emerge and decay continuously. The corona becomes highly structured, with coronal holes appearing at all latitudes and changing shape rapidly. The solar wind becomes more variable, with frequent coronal mass ejections and interplanetary shocks. The heliospheric current sheet develops large amplitude waves, sometimes extending to high latitudes, creating a highly corrugated surface that divides the heliosphere into sectors of alternating polarity. The progression from minimum to maximum takes about 5 years. Sunspots first appear at latitudes around 30 degrees from the equator. As the cycle progresses, new sunspots emerge at progressively lower latitudes, following a pattern known as Sporer's law. By the time solar maximum arrives, sunspots appear primarily within 15 degrees of the equator. The migration of sunspots toward the equator over the solar cycle creates a distinctive butterfly diagram when sunspot latitudes are plotted against time. Only took decades of sunspot mapping to construct the butterfly diagram. The decline from maximum back to minimum also takes about 5 years, though this phase of the cycle is often less regular than the rise. Activity decreases gradually. Sunspot counts decline. The corona simplifies. The heliospheric current sheet flattens. By the end of this decline phase, the Sun has returned to a minimum activity state. But with its magnetic polarity reversed from the previous minimum, the amplitude of the solar cycle varies. Some cycles produce high sunspot counts and intense activity, while others are weaker. The causes of this cycle-to-cycle variability remain uncertain. The Sun's internal dynamo, the process that generates the magnetic field through motions of electrically conducting plasma in the Sun's interior, operates according to complex, non-linear physics that may allow for chaotic variations. Small changes in the initial conditions at the start of a cycle could amplify over time, leading to large differences in the cycle's eventual strength. Solar Cycle 25, which began around 2019, represents the current cycle through which 3 I/Atlas passes. Early predictions suggested this cycle would be relatively weak, similar to the previous cycle, Cycle 24, which was the weakest cycle in a century. But more recent observations hint that Cycle the 25th of May exceed these predictions, with activity rising more quickly than expected. The Sun does not follow predictions precisely. It maintains an element of unpredictability, a reminder that the dynamo process generating the field remains incompletely understood. Only took disagreement between predictions to highlight the limits of current understanding. The solar wind's properties change dramatically over the solar cycle. During solar minimum, the wind's velocity distribution is bimodal. A clear separation exists between slow wind, 300 to 400 km per s, and fast wind, 700 to 800 km per s, with few observations at intermediate speeds. During solar maximum, the distribution becomes more uniform, with wind speeds spread across the entire range. The wind's density also varies, increasing on average during maximum as more plasma is ejected from active regions and coronal mass ejections. Cosmic ray intensity at Earth anti-correlates with solar activity. During solar minimum, when the solar wind is calmer and the heliospheric magnetic field is more regular, cosmic rays penetrate more easily to the inner heliosphere. During solar maximum, when the wind is turbulent and the magnetic field is highly disordered, cosmic rays are scattered more efficiently, reducing their flux at Earth. This modulation affects not only the cosmic rays reaching Earth's surface, but also the radiation environment throughout the heliosphere, with implications for spacecraft operations and for astronauts traveling beyond Earth's protective magnetic field. The Sun's radiative output also varies over the cycle, though by a much smaller amount than the solar wind's variability. Total solar irradiance, EGGADE, the power per unit area reaching Earth, changes by approximately 0.1% between solar minimum and maximum. The change is larger at ultraviolet wavelengths, where emission from the hot corona and transition region dominates. These UV variations affect Earth's upper atmosphere, causing its temperature and density to rise and fall in step with the solar cycle. Satellites in low Earth orbit experience increased drag during solar maximum due to the expanded atmosphere. Only took satellite measurements over multiple cycles to quantify the Sun's radiative variability. 3 I/Atlas will not witness a full solar cycle. The comet's passage through the inner solar system lasts only months, a brief visit spanning a tiny fraction of the 11-year period. The comet arrives during the early rise towards solar maximum, experiences gradually increasing activity, and departs before the peak arrives. The Sun's behavior during this interval represents a single snapshot from the cycle's long evolution, neither fully quiescent nor fully active, but somewhere in between. The comet cannot know that it visits during a particular phase of a cycle. The concept of a cycle requires memory and comparison, the ability to recall past states and recognize their recurrence. The comet has no memory. It responds only to the present moment, to the solar wind flowing past it now, to the sunlight warming its nucleus now. The Sun's history, its cycles, its dynamo, all these remain invisible to the comet, which drifts through space following the laws of gravity and electromagnetic interaction without awareness or anticipation. Human observers, in contrast, possess memory. They track the Sun's behavior across years and decades. They compile statistics, construct models, make predictions. They recognize patterns in the data, the 11-year cycle, the 22-year magnetic cycle, longer-term variations spanning centuries. These patterns help organize understanding, but they do not change the fundamental physical processes. The sun generates its magnetic field. The field drives the solar wind. The wind fills the heliosphere. These processes continue whether observed or not, whether understood or not. Only took human curiosity to track these patterns and seek understanding. Dust grains from 3I/Atlas measure between micrometers and millimeters in size. These grains consist of silicate minerals, carbon compounds, and organic materials assembled in the comet's parent molecular cloud billions of years ago. When sunlight warms the comet's surface, ice sublimes and entrains dust particles in the expanding gas, lifting them away from the nucleus. Once free, the grains follow trajectories determined by solar gravity, solar radiation pressure, and the Lorentz force acting on charged grains in the presence of the interplanetary magnetic field. Small grains experience stronger effects from radiation pressure than large grains. Radiation pressure arises from the momentum carried by photons. When photons strike a dust grain and are absorbed or scattered, they transfer momentum to the grain, pushing it away from the sun. The acceleration produced by this pressure depends on the grain's cross-sectional area and its mass. Smaller grains have a larger area-to-mass ratio, so they accelerate more strongly. Grains smaller than a few micrometers can be pushed outward faster than they fall inward under solar gravity, creating highly elongated trajectories that curve away from the sun's direction. Only took observations of comet dust tails to infer the size distribution of escaping grains. Larger grains, in contrast, follow trajectories more strongly influenced by solar gravity. Radiation pressure still acts on them, but it cannot overcome the gravitational pull. These grains fall sunward after leaving the comet, though their paths curve slightly away from the radial direction due to the small radiation pressure component. Over time, the grains drift into orbits around the sun, becoming part of the zodiacal cloud, the diffuse disk of dust that pervades the inner solar system and scatters sunlight, creating the faint glow called zodiacal light visible from Earth shortly after sunset or before sunrise. Dust grains can acquire electrical charge through several mechanisms. Photoelectric emission occurs when ultraviolet photons strike the grain and eject electrons from its surface, leaving the grain positively charged. Secondary electron emission occurs when energetic electrons from the solar wind strike the grain, knocking out additional electrons. Plasma currents can flow to or from the grain, depending on whether electrons or ions strike the surface more frequently. The balance of these processes determines the grain's equilibrium charge, which typically ranges from negative values in shadowed regions to positive values in sunlight. Charged grains respond to the interplanetary magnetic field through the Lorentz force. This force acts perpendicular to both the grain's velocity and the magnetic field direction, causing the grain to drift sideways. The strength of the drift depends on the grain's charge, the magnetic field strength, and the grain's velocity. For typical interplanetary conditions, the magnetic deflection is small compared to gravitational and radiation pressure effects, but it can accumulate over time, causing grains to disperse in directions perpendicular to the radial and anti-radial directions from the sun. Only took spacecraft measurements of dust impacts to characterize grain charge states. The trajectories of dust grains from 3I/Atlas differ subtly from trajectories of grains released by solar system comets. Because 3I/Atlas follows a hyperbolic orbit, its velocity relative to the sun exceeds the escape velocity. Grains released from the comet inherit this excess velocity, even after accounting for solar gravity and radiation pressure. The grains continue moving outward from the solar system on hyperbolic trajectories of their own. They will not return. They will not contribute to the zodiacal cloud. They will travel through the heliosphere, cross the heliopause, and enter interstellar space, becoming part of the dust population that drifts between stars. The dust production rate of 3I/Atlas is estimated through observations of the dust tail's brightness and extent, models of light scattering by dust grains, combined with assumptions about grain size distribution and composition, allow observers to infer how much dust the comet releases per second. Current estimates suggest a production rate of tens to hundreds of kilograms per second, modest compared to some active comets, but sufficient to create a visible dust tail. The composition of the dust grains can be inferred from spectroscopy. Silicate minerals exhibit characteristic absorption and emission features at mid-infrared wavelengths. Carbon compounds absorb light at ultraviolet and visible wavelengths, giving the dust a dark appearance. Organic molecules may show spectral features in the infrared, though these features are often weak and difficult to detect. By comparing the observed spectrum of 3I/Atlas's dust to laboratory spectra of candidate materials, scientists constrain the grain composition. Grains from interstellar comets offer a unique opportunity. Unlike grains from solar system comets, which formed in the Sun's protoplanetary disk, grains from interstellar comets formed in a different stellar environment. Comparing the two populations can reveal similarities or differences in the chemical processes that operated in the two disks. So far, observations of 1I/Oumuamua and 2I/Borisov suggested that interstellar comets may not differ greatly from solar system comets in composition, but the sample size remains too small for definitive conclusions. Only took 3 interstellar objects to begin comparative studies. The dust grains carry isotopic signatures inherited from their formation environment. The ratios of different isotopes of oxygen, carbon, nitrogen, and other elements depend on the nuclear reactions that occurred in previous generations of stars and on the chemical processes that operated in the molecular cloud where the comet's parent star formed. These ratios are extremely difficult to measure in dust grains from comets without collecting samples and analyzing them in the laboratory. Remote observations provide only limited isotopic information, typically restricted to gas phase molecules in the coma. Some dust grains released by 3I/Atlas will eventually be captured by Earth. Grains on trajectories that happen to intersect Earth's orbit will enter the atmosphere at high velocity, tens of kilometers per second, and heat to incandescence through friction with air molecules. Most grains vaporize completely, contributing to the meteor phenomenon observed when small particles burn up in the atmosphere. A few grains, if they are unusually strong or follow slower trajectories, may survive the passage through the atmosphere and reach Earth's surface as micrometeorites. Micrometeorites accumulate on Earth's surface at a rate of several tens of tons per day. Most originate from asteroids and comets within the solar system, but a small fraction may come from interstellar sources. Distinguishing interstellar micrometeorites from solar system ones requires detailed compositional and isotopic analysis, which is challenging for particles measuring only tens of micrometers across. Nevertheless, scientists continue searching for interstellar grains in collections of micrometeorites recovered from Antarctic ice, ocean sediments, and high-altitude aircraft filters. Only took decades of micrometeorite collection to build libraries of extraterrestrial dust. The dust grains from 3I/Atlas disperse as they travel through the heliosphere. Solar radiation pressure, magnetic deflections, and gravitational perturbations from planets cause grains that left the comet nearly simultaneously to follow diverging paths. Over months and years, a cloud of grains spreads out along the comet's trajectory and perpendicular to it, forming a diffuse stream that gradually loses coherence. Eventually, individual grains become indistinguishable from the background population of interstellar dust grains that pervade the galaxy. The lifetime of a dust grain in space depends on its size and the environment through which it travels. Small grains, micrometers in size, can be destroyed by sputtering, the gradual erosion of surface atoms by impacts with solar wind ions. This process operates slowly, removing perhaps a few nanometers of material per million years. But over the grain's lifetime, the cumulative effect can be significant. Larger grains are less vulnerable to sputtering, but may be shattered by collisions with other grains or with micrometeorites traveling at high relative velocities. Grains in interstellar space face additional hazards. Cosmic rays passing through a grain deposit energy that can alter its structure, breaking chemical bonds and creating defects in the crystal lattice. Ultraviolet photons from distant stars slowly process organic materials on the grain's surface, converting complex molecules into simpler compounds. These processes gradually modify the grain's properties over timescales of millions to billions of years, erasing some of the information about its origin while creating new features that reflect its long journey through space. Only took laboratory experiments simulating space weathering to understand these modification processes. The grains from 3I/Atlas carry no labels identifying their origin. Once they merge with the interstellar dust population, they become anonymous, indistinguishable from grains ejected by other comets in other stellar systems. Their shapes, their compositions, their isotopic ratios, all these properties fall within the broad range exhibited by interstellar grains in general. The grains contribute to the galaxy's reservoir of solid material, participating in the slow cycle through which matter moves from stars to interstellar space, from clouds to new stars, repeatedly over billions of years. The comet itself continues to release grains as it approaches perihelion. The dust production rate increases with decreasing distance from the Sun, driven by the higher solar flux and the resulting higher temperatures on the comet's surface. More ice sublimes, lifting more dust. The dust tail brightens and lengthens. Observers on Earth capture images showing the tail's evolution, tracking its changing appearance as the comet responds to increasing solar heating. But the total mass lost to dust remains small compared to the comet's overall mass. Even if the comet releases dust at a rate of 100 kilograms per second for 100 days, roughly the duration of enhanced activity near perihelion, the total mass lost amounts to only about 1 million tons, for a comet measuring 1 kilometer across with a density of 600 kilograms per cubic meter. The total mass is approximately 300 billion tons. The mass lost to dust represents a tiny fraction, roughly 0.0003% of the comet's total mass. Only took basic physics to calculate that even active comets lose a small fraction of their mass per orbit. The dust grains serve as traces of the comet's activity and as probes of the solar wind environment. Their trajectories encode information about the radiation pressure field, the gravitational field, and the electromagnetic forces acting on charged particles. By measuring the dust tail's shape and brightness distribution, scientists infer the size distribution of grains, the dust production rate, and the grain's velocity distribution at the moment of release. These inferences rely on models that account for the various forces and that assume specific properties for the grains. The models sometimes disagree with observations, revealing gaps in understanding. Predicted tail shapes may not match observed shapes exactly. Predicted grain sizes may not match the sizes inferred from other techniques. These discrepancies drive improvements in the models, prompting scientists to include additional physical processes or to refine existing ones. The cycle of observation, modeling, and refinement continues, gradually building a more complete and accurate picture of how cometary dust behaves. Dust from 3I/Atlas will travel through interstellar space for billions of years, long after the comet itself has evaporated or fragmented. The grains drift through the galactic disk, occasionally passing through molecular clouds, sometimes being incorporated into new protoplanetary disks. A few grains may eventually find themselves orbiting a new star, mixed with fresh material in a forming planetary system. The history these grains carry, their origin in a different stellar system, their passage through our solar system, their long journey through interstellar space, will be lost. overwritten by new processes in the new environment, only took one comet's passage to scatter 1 billion dust grains across the galaxy. The Parker spiral describes the three-dimensional shape of the interplanetary magnetic field, named after Eugene Parker, who predicted its form in the late 1950s. The spiral results from the combination of the Sun's rotation and the radial outflow of the solar wind. Near the Sun, magnetic field lines point radially outward from the surface, but as the solar wind carries these field lines into space, the Sun's rotation causes them to twist, creating a spiral pattern that wraps around the Sun like water streams from a rotating lawn sprinkler. The mathematics of the Parker spiral follows from simple assumptions. The solar wind flows radially outward at constant velocity. The Sun rotates with constant angular velocity. Magnetic field lines are frozen into the plasma, moving with it. From these assumptions, one can derive that field lines trace out logarithmic spirals in the equatorial plane. The angle between the field line and the radial direction increases with distance from the Sun. Near the Sun, the field is nearly radial. Far from the Sun, the field lines wrap tightly around the Sun, approaching a purely azimuthal orientation. Only took Parker's original 1958 paper to predict this geometry before any observations confirmed it. At Earth's orbit, 1 astronomical unit from the Sun, the typical angle between the magnetic field and the radial direction is approximately 45 degrees. The field points outward and sideways, trailing behind the Sun's rotation. Sometimes the angle is larger, sometimes smaller, depending on the solar wind's velocity at that moment. Faster wind produces a more radial field. Slower wind produces a more tightly wound spiral. The average angle of 45 degrees reflects the typical solar wind speed of 400 kilometers per second and the Sun's rotation period of 27 days. At 5 astronomical units, near Jupiter's orbit and the current location of 3y/Atlas, the angle increases to approximately 65 degrees. The field lines wrap more tightly around the Sun. A spacecraft at this distance observes that the magnetic field points primarily in the azimuthal direction, tangent to circles centered on the Sun, with only a modest radial component. The azimuthal component carries the imprint of the Sun's rotation, connecting plasma at Jupiter's orbit back to the region on the Sun's surface from which it originated days earlier. The Parker spiral is not perfectly smooth. Real solar wind velocity varies with time and location. Stream-stream interactions create compressions and rarefactions in the flow. Coronal mass ejections disrupt the steady-state configuration. These variations distort the ideal spiral geometry, creating kinks, waves, and discontinuities in the field. Spacecraft measurements reveal that the magnetic field direction fluctuates continuously on timescales ranging from seconds to hours. Superimposed on the average spiral pattern, only took in situ measurements from multiple spacecraft to reveal the field's variability. The spiral exists in 3 dimensions, not just in the equatorial plane, above and below the solar equator. Field lines still follow approximately the same spiral shape, but they also possess a component pointing away from the equatorial plane, northward or southward, depending on the magnetic polarity of the region. This out-of-plane component becomes more significant at higher latitudes, where the flow of the solar wind has a meridional component carrying plasma toward or away from the solar poles. The heliospheric current sheet divides regions where the magnetic field has opposite polarity. On one side of the sheet, field lines spiral outward with one orientation. On the other side, they spiral outward with the opposite orientation. The current sheet itself is a thin layer where the field rotates smoothly from one orientation to the other. In the ideal Parker model, the current sheet lies in the solar equatorial plane. In reality, the sheet warps above and below the equator, creating a surface that resembles a ballerina's twirling skirt when viewed from above the solar poles. Spacecraft crossing the heliospheric current sheet measure a reversal in the magnetic field's radial or latitudinal component. Depending on the spacecraft's location and trajectory, the crossing is sometimes sharp, occurring over a few seconds, and sometimes gradual, spread over minutes or hours. The structure of the current sheet at small scales remains an active research topic. High-resolution measurements reveal layers, oscillations, and embedded waves within the sheet, suggesting that multiple physical processes contribute to its structure. Only took crossings from dozens of spacecraft at various locations to map the current sheet's three-dimensional shape. The magnetic field in the spiral carries information from the Sun to the outer heliosphere. Particles can stream along field lines with relative ease, spiraling around the lines as they move. Electrons, being lighter and more mobile, travel along the lines faster than ions. These streaming particles create currents that help maintain the field structure. The currents themselves generate secondary magnetic fields, adding complexity to the overall configuration. Magnetic flux, the amount of field threading through a surface, is conserved in the ideal Parker model. As the solar wind expands outward, the area through which field lines pass increases, so the magnetic field strength must decrease to keep the total flux constant. Near the Sun, the field strength is measured in hundreds of nanoteslas. At 1 astronomical unit, it weakens to about 6 nanoteslas on average. At 5 astronomical units, it drops to below 1 nanotesla. At the heliopause, more than 100 astronomical units from the Sun, the field strength falls to about 0, 1 nanoteslas, approaching the strength of the interstellar magnetic field. The decrease in field strength with distance follows from the geometry of the expanding solar wind. For a perfectly radial field, the strength would decline as the inverse square of the distance, but the spiral configuration introduces an additional factor. The total field strength declines more slowly than inverse square because the azimuthal component does not decrease as rapidly as the radial component. Detailed models and spacecraft measurements confirmed that the field strength falls approximately as distance to the power of negative 1.5 in the ecliptic plane. Only took measurements at multiple heliocentric distances to confirm the field's radial dependence. Turbulence modifies the Parker spiral on small scales. Large-scale Alfvén waves and magnetohydrodynamic turbulence create fluctuations in the field that cascade from large scales to small scales, where dissipation processes convert wave energy into heat. The turbulent fluctuations are superimposed on the average spiral configuration, creating a magnetic field that varies continuously in time and space. The power spectrum of these fluctuations, the amount of fluctuation energy at different frequencies or wave numbers, follows characteristic power laws that reflect the turbulent cascade dynamics. The spiral rotates with the Sun. An observer far above the solar North Pole looking down would see the spiral pattern rotating once every 27 days. The pattern fixed relative to the Sun, but sweeping through space as the Sun turns. Features in the pattern: fast wind streams, slow wind regions, coronal mass ejection remnants, rotate with the Sun, creating periodic variations at fixed locations in the heliosphere. This corrotation is responsible for the 27-day recurrence of geomagnetic activity on Earth during certain phases of the solar cycle. 3 I/Atlas moves through the Parker spiral unaware of its global geometry. The comet experiences only the local magnetic field, the field at its current location, pointing in a particular direction, with a particular strength. The comet cannot perceive that this local field is part of a vast spiral structure connecting it back to the Sun's surface, nor that the structure rotates with the Sun, nor that it extends throughout the heliosphere. These are human constructions. Mental models built from scattered observations and physical reasoning. Only took human intelligence to infer the global structure from local measurements. The Parker spiral will persist as long as the sun rotates and produces solar wind. The geometry depends only on these two factors and on the assumption of radial flow, which holds approximately throughout most of the heliosphere. Changes in solar wind speed alter the tightness of the spiral, but not its basic form. The spiral is a fundamental feature of the heliosphere's magnetic architecture, as enduring as the solar wind itself. Whether 3I/Atlas generates a bow shock remains uncertain. A bow shock forms upstream of an obstacle when the solar wind, traveling at supersonic speed, encounters the obstacle and must decelerate to flow around it. For Earth, this obstacle is the planet's magnetic field, which prevents the solar wind from reaching the surface. For comets, the obstacle is the ionized coma, the cloud of ions surrounding the nucleus. But not all comets produce bow shocks. The comet must generate sufficient ions to create a large enough obstacle. Small comets with weak outgassing may not reach the critical threshold. The criterion for bow shock formation involves comparing two length scales. The first is the ion production rate converted to a characteristic size, the radius within which ion production significantly loads the solar wind with mass. The second is the ion gyroradius, the radius of the circular path an ion traces as it spirals around a magnetic field line. If the first length scale exceeds the second by a sufficient factor, the ions collectively act as an obstacle, and a shock forms upstream. If not, the ions are picked up individually by the solar wind without creating a coherent shock structure. Only took missions to multiple comets to establish the conditions for shock formation. Comet Halley, observed by spacecraft in 1986, displayed a clear bow shock. The shock stood off from the nucleus by approximately 100,000 kilometers, forming a curved surface where the solar wind transitioned from supersonic to subsonic flow. Instruments on the Giotto spacecraft detected the shock crossing through sudden jumps in plasma density, temperature, and magnetic field strength. The shock's location and strength varied as the comet's outgassing rate changed and as solar wind conditions fluctuated. Smaller comets observed by other missions showed weaker or absent shocks. The criterion depends sensitively on the comet's gas production rate, which varies over many orders of magnitude among different comets and changes for a given comet as its distance from the Sun changes. Near perihelion, when solar heating maximizes outgassing, a comet is most likely to produce a shock. Far from the Sun, when outgassing weakens, any existing shock may vanish as the comet no longer produces enough ions to form a sufficient obstacle. For 3I/Atlas, estimates of the gas production rate suggest the comet lies near the boundary between shock-forming and non-shock-forming regimes. If the production rate exceeds a critical value, approximately 10 to the 27th molecules per second of water or equivalent species, a shock should form. If the production rate falls below this value, no shock will appear. Observations so far indicate production rates in the uncertain range, neither clearly above nor clearly below the threshold. The uncertainty arises from multiple sources. The gas production rate must be inferred from brightness measurements and spectroscopic observations, both of which require assumptions about the comet's coma structure, the excitation processes affecting molecules, and the distribution of dust. Different analysis methods yield different production rate estimates, sometimes disagreeing by factors of 2 or more. Additional uncertainty comes from the solar wind conditions at the comet's location. Variations in wind speed and density affect the shock formation criterion. Only took decades of comet observations to recognize how uncertain production rate estimates can be. If a shock forms, it will be weak compared to planetary bow shocks. The compression ratio, the factor by which density and magnetic field strength increase across the shock, will be modest, perhaps only 2 or 3. The shock will also be highly variable, responding to fluctuations in the comet's outgassing and in the solar wind. The shock surface may develop ripples, waves, and local distortions as it adjusts to changing conditions. These features make the shock difficult to detect from afar and challenging to model theoretically. No spacecraft will fly through 3I/8less's interaction region to measure whether a shock exists. The comet's hyperbolic trajectory and its arrival time prevented mission planners from designing a rendezvous. Remote observations must suffice. These observations can provide indirect evidence for a shock through measurements of radio emission, energetic particles, or ultraviolet emission patterns that might indicate shock-accelerated particles or shock-heated plasma. But such indirect signatures are subtle and open to alternative interpretations. Models of the 3I/Atlas interaction predict the bow shock's location if one forms. The shock would stand off from the nucleus by a distance depending on the ion production rate and the solar wind ram pressure, the product of density and velocity squared, for estimated conditions. The standoff distance might range from 50,000 to 200,000 kilometers. This distance is small compared to the comet's sun distance of 5 astronomical units, but large compared to the nucleus size of 1 kilometer. The shock's shape would resemble a paraboloid, with the nose pointing toward the sun and the flanks curving back to wrap around the ionized coma. The shock surface would not be symmetric. Variations in the solar wind's velocity and magnetic field direction would create asymmetries, tilting the shock and distorting its shape. The shock might also interact with structures in the solar wind, stream interfaces, current sheets, discontinuities, producing localized distortions and perhaps temporary disruptions. Only took magnetohydrodynamic simulations to predict these complex shock geometries. Downstream of the shock, if it exists, the solar wind properties change. The flow slows from supersonic to subsonic speeds. The density increases. The temperature rises. The magnetic field strengthens and may change direction as it drapes around the ionized coma. These changes create a region called the shock sheath, separating the shock from the inner boundary of the comet's interaction region. Within the sheath, the plasma and field evolve as they flow toward the comet, interacting with freshly produced ions and adjusting to the changing geometry. The absence of a shock would not mean the absence of an interaction. Even without a shock, the solar wind would still encounter the ionized coma, still load mass from the comet's outgassing, still drape magnetic field lines around the obstacle. The interaction would simply be more gradual, lacking the abrupt jump in properties that characterizes a shock. Observations so far do not definitively resolve whether a shock exists, and the question may remain unanswered unless the comet's activity increases substantially or new observations provide clearer signatures. The uncertainty reflects the nature of scientific investigation. Not every question receives a definitive answer. Some observations remain ambiguous, consistent with multiple interpretations. In such cases, scientists express the uncertainty honestly, presenting the evidence and the range of possible conclusions. For 3I/Atlas, the bow shock question may eventually be resolved, or it may persist as one of the unanswered details of this particular comet's passage through the solar system. Only took one interstellar comet to pose this unresolved question. The interstellar medium fills the space between stars with extremely dilute gas and dust. In the solar neighborhood, the region of the galaxy within a few hundred light-years of the Sun, the interstellar medium consists primarily of neutral hydrogen atoms, with smaller amounts of helium, ionized hydrogen, and trace quantities of heavier elements. The typical density is approximately 0.1 atoms per cubic centimeter, though this value varies by orders of magnitude depending on whether the region is a cold molecular cloud, a warm neutral medium, or a hot ionized medium. 1 atom per cubic centimeter represents an extraordinarily good vacuum by terrestrial standards. The best laboratory vacuums on Earth achieve densities of perhaps 1 million atoms per cubic centimeter, still far denser than interstellar space. The mean free path of an atom in the interstellar medium, the average distance it travels before colliding with another atom, exceeds 100,000 astronomical units, or about 1 light-year. Collisions between atoms are rare. Most interactions occur through electromagnetic forces operating over long distances rather than through direct contact. Only took decades of astronomical observations to measure the interstellar medium's density. The temperature of the interstellar medium varies depending on its phase. Cold molecular clouds, where stars form, have temperatures of 10 to 20 Kelvin. The warm, neutral medium, which fills much of the galactic disk between clouds, reaches temperatures of several thousand Kelvin. The hot ionized medium, heated by supernova explosions and stellar winds, achieves temperatures exceeding 1 million Kelvin. Despite these high temperatures, the energy density remains low because the particle density is so small. A human could pass through million Kelvin plasma in interstellar space without feeling warm, because so few particles would strike the body per second. The local interstellar medium surrounding the solar system is part of a larger structure called the local bubble, a region of low density, hot plasma extending roughly 300 light-years in diameter. This bubble was carved out by supernova explosions over the past 10 to 20 million years. The explosions heated and dispersed the gas that previously filled this region, leaving behind a cavity with a density several times lower than the galactic average. The Sun currently resides near the edge of the local bubble, in a region called the local interstellar cloud. The local interstellar cloud is a small, dense feature embedded within the local bubble. Its density is approximately 0, 3 atoms per cubic centimeter, higher than the bubble's average but still extremely tenuous. The cloud's temperature is approximately 6,000 Kelvin, making it a warm, partially ionized medium. The cloud's extent is uncertain, but it likely spans several light-years. The solar system has been passing through this cloud for the past few tens of thousands of years and will continue to do so for tens of thousands of years into the future. Only took observations of nearby stars' absorption spectra to map the local interstellar cloud. The interstellar medium contains a magnetic field threading through the gas in the solar neighborhood. The field strength is approximately 3 microgauss, or 0.3 nanoteslas, comparable to the magnetic field in the outer heliosphere. The field's direction is roughly aligned with the plane of the galaxy, but local variations and turbulence create regions where the field points in other directions. The field influences the motion of charged particles in the interstellar medium and affects the structure of the heliosphere's boundary. Dust grains compose a small but significant fraction of the interstellar medium's mass. These grains, typically 0.1 micrometers in size, consist of silicates, carbon compounds, and ices. The grains absorb and scatter starlight, creating extinction and reddening effects that astronomers must account for when observing distant objects. The grains also play a crucial role in interstellar chemistry, providing surfaces on which molecules can form through reactions that would not occur in the gas phase. The interstellar medium is not static. Gas flows through it, driven by stellar winds, supernova explosions, and the rotation of the galaxy. The solar system moves through the local interstellar medium at approximately 26 kilometers per second, creating a relative wind that the heliosphere must deflect. This motion has varied over the history of the solar system as the Sun orbits the galactic center and passes through different regions of the galaxy over millions of years. The Sun's path through the galaxy takes it through regions of varying interstellar medium density. When the Sun enters a denser cloud, the ram pressure on the heliosphere increases, compressing the heliopause inward. When the Sun exits into a less dense region, the heliosphere expands. These variations in heliospheric size may affect the flux of galactic cosmic rays reaching Earth, potentially influencing climate through effects on cloud formation, though the magnitude of this effect remains controversial. Only took geological and ice core records spanning millions of years to search for correlations between interstellar medium conditions and Earth's climate. The composition of the interstellar medium reflects the cumulative history of nucleosynthesis in stars. Hydrogen and helium were produced in the Big Bang. Heavier elements, carbon, nitrogen, oxygen, iron, and others, were forged in stellar interiors through nuclear fusion and ejected into space through stellar winds and supernova explosions. Each generation of stars enriches the interstellar medium with heavy elements, gradually increasing the metallicity, the fraction of elements heavier than hydrogen and helium. The Sun formed from interstellar medium material approximately 4.6 billion years ago. The composition of the solar system, measured through spectroscopy of the Sun and analysis of meteorites, reflects the composition of the interstellar medium at that time and location in the galaxy. Comparing the solar composition to the current local interstellar medium composition reveals that the interstellar medium has been enriched with heavy elements since the Sun's formation, consistent with continued star formation and evolution in the galactic disk. 3I/Atlas originated from interstellar medium material in a different part of the galaxy. The comet's formation occurred in a molecular cloud that collapsed to form a star and planetary system, probably within the past few billion years. The comet was ejected from that system through gravitational interactions, perhaps with a giant planet, and wandered through interstellar space until its trajectory happened to bring it near the Sun. The journey through interstellar space exposed the comet's surface to cosmic rays, to ultraviolet photons from distant stars, and to impacts with interstellar dust grains. Only took one interstellar comet's composition to begin comparing chemistry across stellar systems. The interstellar medium near 3I/Atlas's parent star may have differed from the local interstellar medium near the Sun. Variations in metallicity, isotopic ratios, and molecular abundances across the galaxy create regional differences in the properties of forming planetary systems. These differences might show up in the composition of interstellar comets, providing clues about the chemical evolution of different galactic regions. So far, observations of interstellar objects have not revealed major compositional differences, suggesting that the processes governing comet formation may be relatively universal. The density of the interstellar medium affects the heliosphere's size and structure. In denser regions, the heliosphere compresses. In less dense regions, it expands. The transition from one regime to another occurs gradually, over time scales of thousands to millions of years, as the solar system moves through regions of varying density. The Voyager spacecraft, having crossed the heliopause, now measure properties of the local interstellar medium directly, providing ground truth for models of the interstellar medium structure. The interstellar medium will persist as long as the galaxy exists, constantly recycled through star formation and death. Gas in the medium collapses under gravity to form new stars. Stars process the gas through fusion, producing heavier elements. Stellar winds and supernova explosions return enriched material to the medium. The cycle continues, gradually converting hydrogen to helium and heavier elements, slowly changing the galaxy's composition over billions of years. By the time solar wind reaches Jupiter's orbit, roughly 5 astronomical units from the Sun, its properties have evolved from their coronal origins. The wind's velocity typically remains between 300 and 700 kilometers per second, depending on whether the wind originated from slow or fast solar wind source regions, but the density has decreased significantly. At 1 astronomical unit, near Earth, the wind's proton density averages about 5 particles per cubic centimeter. At 5 astronomical units, the density drops to approximately 0, 2 particles per cubic centimeter, following roughly an inverse square law reflecting the expansion of the wind into ever larger volumes of space. The temperature structure of the solar wind at Jupiter's distance differs from expectations based on adiabatic expansion alone. If the wind expanded without gaining or losing energy, its temperature would decrease rapidly with distance, proportional to distance to the power of -4/3. But measurements show that the actual temperature decline is slower, indicating that energy continues to be added to the wind as it flows outward. The energy sources may include dissipation of turbulent fluctuations, heating by waves, and possibly small-scale magnetic reconnection events. Only took measurements from spacecraft at multiple heliocentric distances to reveal this unexpected heating. The magnetic field strength at Jupiter's orbit averages approximately 0.5 to 1 nanoteslas, compared to about 6 nanoteslas at Earth's orbit. The Parker spiral geometry persists, with the magnetic field making a large angle to the radial direction, typically 60 to 70 degrees. The field's variability increases with distance from the Sun as turbulent fluctuations grow in amplitude and as stream-stream interactions create large-scale structures that propagate through the heliosphere. Jupiter itself affects the solar wind flowing past it. The planet's enormous magnetosphere, the region dominated by Jupiter's intrinsic magnetic field, extends tens of Jovian radii upstream toward the Sun and hundreds of radii downstream in the planet's magnetotail. The solar wind must deflect around this obstacle, creating a bow shock upstream of the magnetosphere where the supersonic wind slows and heats. Jupiter's magnetosphere is the largest permanent structure in the solar system after the heliosphere itself, and it significantly perturbs the solar wind in its vicinity. The interaction between the solar wind and Jupiter's magnetosphere differs fundamentally from the interaction between the wind and a comet. Jupiter's magnetic field, generated by convective motions in the planet's metallic hydrogen interior, is strong enough to prevent the solar wind from reaching the planet's atmosphere. The comet has no intrinsic magnetic field and relies on its ionized coma to deflect the wind. Jupiter's magnetosphere is dynamic, driven by the planet's rapid rotation and by the volcanic activity on its moon Io, which injects copious ions into Jupiter's magnetic environment. The comet's interaction is passive, shaped entirely by the comet's outgassing and the properties of the ambient wind. Only took the Pioneer and Voyager spacecraft to reveal Jupiter's magnetosphere's vast extent. Beyond Jupiter, the solar wind continues outward towards Saturn, Uranus, Neptune, and eventually the termination shock in the outer heliosphere. At each successive planet, the wind's density is lower, its temperature structure more complex, its variability greater. Saturn, at 10 astronomical units, experiences wind densities of roughly 0.05 particles per cubic centimeter. Neptune, at 30 astronomical units, sees densities of approximately 0.005 particles per cubic centimeter. The wind thins to an imperceptible whisper, yet it remains supersonic, still carrying energy and momentum away from the Sun. The wind's influence extends to all objects in the solar system. Asteroid surfaces are weathered by solar wind impacts, gradually darkening and altering their reflectance spectra. The atmospheres of planets without strong magnetic fields, Venus, Mars, are slowly eroded by the wind, which strips atoms and molecules from the upper atmosphere and carries them away into space. Even Earth's atmosphere experiences erosion, though at a much lower rate because Earth's magnetic field shields most of the atmosphere from direct solar wind contact. 3I/Atlas, at 5 astronomical units, experiences solar wind conditions intermediate between the inner and outer heliosphere. The wind remains strong enough to produce a visible plasma tail and to interact significantly with the comet's coma, but the wind's density is lower than it would be closer to the Sun, reducing the rate of ion production through charge exchange and diminishing the brightness of the plasma tail. The magnetic field, though weaker, retains sufficient strength to drape around the coma and shape the tail's structure. The wind at this distance carries fluctuations on many time scales. High-frequency fluctuations, with periods of seconds to minutes, reflect turbulent cascades and plasma waves. Low-frequency fluctuations, with periods of hours to days, reflect stream-stream interactions and the passage of large-scale structures. The comet samples all these fluctuations, its plasma tail responding like a flag in a variable wind, brightening and dimming, elongating and compressing. As conditions change, only took continuous monitoring of the comet to observe these tail variations in response to wind changes. Comparisons between the solar wind at different heliocentric distances reveal how the wind evolves. Near the Sun, the wind consists of discrete streams with sharp boundaries and strong velocity gradients. At 1 astronomical unit, these streams interact, creating correlating interaction regions where fast streams compress slower streams ahead of them. At 5 astronomical units, the interaction regions have matured, with smooth compression regions and rarefaction regions alternating as the structures rotate with the Sun. Beyond 10 astronomical units, the wind becomes more homogenized, its structure averaged out over the long transit time from the Sun. The wind's composition also evolves with distance. The ratio of alpha particles to protons remains roughly constant, since both species travel at nearly the same velocity once they are far from the Sun, but the charged states of heavier ions can change through electron capture from neutral atoms, either from the interstellar medium penetrating into the heliosphere or from neutral gas produced locally by charge exchange. These changes in ion charge states provide additional traces of the wind's history and of its interaction with neutral gas. The wind slows gradually as it approaches the termination shock. The solar wind's velocity remains roughly constant through most of the inner and middle heliosphere, but in the outer heliosphere, gravitational deceleration and pressure gradients begin to slow the flow. By the time the wind reaches the termination shock at 90 to 100 astronomical units, its velocity has decreased by perhaps 10% from its value in the inner heliosphere. The shock then slows the wind much more dramatically, reducing it from supersonic to subsonic flow. Beyond the termination shock lies the heliosheath, and beyond that, the heliopause. But 3I/Atlas will never see these distant boundaries. The comet's trajectory carries it through the inner heliosphere, past the Sun, and back outward on a path that will take it beyond the planets, but not nearly as far as the heliopause. The comet will exit the solar system while still deep within the heliosphere, entering a different regime where the solar wind remains supersonic and the Sun's influence, though weakening, persists. Only took billions of kilometers of travel to move from one regime of the heliosphere to another. The wind's journey from the Sun to Jupiter and beyond represents a continuous transformation. What begins as a hot, dense, highly variable flow emerging from the solar corona becomes a cool, tenuous, evolving flow in the outer heliosphere. The transformation unfolds over days, weeks, and months as parcels of plasma travel outward, expand, cool, interact with other parcels, and eventually reach the heliosphere's boundaries. The wind carries with it the Sun's magnetic field, the Sun's energy, and information about conditions in the corona days or weeks earlier. It is a river flowing through space, connecting the Sun to the far reaches of its domain. 3I/Atlas continues outward after perihelion, moving away from the Sun at a velocity that will carry it beyond the solar system entirely. The comet's closest approach to the Sun, its perihelion, occurs at approximately 1.2 astronomical units, closer than Earth's orbit but not dramatically so. At this distance, solar heating reaches its maximum for this particular passage. Ice sublimation accelerates. Gas production peaks. The plasma tail brightens and lengthens. Dust production increases. The comet becomes, for a brief time, more active than at any other point in its journey through the inner solar system. But perihelion passes quickly, lasting only days at the comet's velocity. The comet moves at 40 kilometers per second relative to the Sun near perihelion, covering roughly 3 million kilometers per day. Within a week, the distance from the Sun increases noticeably. Within a month, the comet has receded to nearly 2 astronomical units. The solar flux decreases. Surface temperatures on the nucleus decline. Outgassing slows. The coma thins. The plasma tail dims and contracts. The brief peak of activity fades into a long, slow decline that will continue for months until the comet's activity ceases entirely. The comet's hyperbolic trajectory ensures it will never return. Unlike comets born in the solar system, which orbit the Sun in elliptical paths and may return after decades, centuries, or millennia. 3I/Atlas follows a path that opens outward to infinity. Its orbital energy is positive. The sum of kinetic and gravitational potential energy exceeds zero, meaning the comet possesses more than enough velocity to escape the Sun's gravitational pull. No force will turn it around. No future perihelion awaits. The comet passes through once and continues into the galaxy. Only took precise orbital determination to confirm the hyperbolic nature beyond doubt. The data embedded in the comet's evaporating ice will never be fully retrieved. As the comet's distance from the Sun increases beyond 5 astronomical units, beyond 10, beyond 20, observations become increasingly difficult. Ground-based telescopes lose sight of the comet as its brightness fades below detection thresholds. Space telescopes may track it slightly longer, but eventually even they will lose the signal in the noise of background sources. The comet will disappear from human view while still within the outer solar system, its subsequent journey unobserved and unrecorded. The ice evaporating from the nucleus during the comet's passage through the inner solar system carries isotopic ratios that encode information about the chemistry of the comet's formation region. Water molecules, carbon monoxide molecules, nitrogen molecules. Each species possesses a characteristic ratio of isotopes that depends on the temperature, density, and composition of the molecular cloud where the comet formed. These ratios can differ between stellar systems due to variations in the local history of nucleosynthesis and chemical processing. Spectroscopic observations during the comet's visible passage capture some of this information. Measurements of the deuterium to hydrogen ratio in water, for instance, constrain the temperature of the region where water ice condensed. Measurements of the carbon 12 to carbon-13 ratio provide clues about the chemical evolution of the parent molecular cloud. Measurements of the nitrogen-15 to nitrogen-14 ratio shed light on the processes that incorporated nitrogen into solid material. These measurements, combined with similar data from solar system comets, allow comparisons that test whether comet formation proceeds similarly in different stellar environments. Only took decades of isotopic measurements in solar system comets to establish baseline values for comparison. The comet carries this data physically in the structure of its ice. Each molecule in the nucleus contains atoms with specific isotopic compositions. The distribution of isotopes throughout the nucleus may not be uniform. Layering or heterogeneity could exist, reflecting the comet's accretion history or subsequent processing. As the comet evaporates, it samples different layers, potentially revealing variations in composition with time or location within the nucleus. But this detailed sampling requires close-range observations or sample return, neither of which will occur for 3I/Atlas. The solar wind data embedded in the comet's environment will disperse as the comet recedes. The plasma tail, shaped by the solar wind and magnetic field, traces conditions in the heliosphere at the specific time and location of the comet's passage. The tail structure encodes information about wind velocity, density, magnetic field strength, and direction, and the presence or absence of transient structures like coronal mass ejections and stream interaction regions. This information exists momentarily, written in plasma and magnetic field, but it dissipates as the tail plasma mixes with the surrounding solar wind and as the comet stops producing new ions. Remote observations capture snapshots of the tail's structure at various times during the comet's passage. These snapshots, though incomplete, preserve some of the information about solar wind conditions. By analyzing the tail's brightness, length, shape, and variability, scientists infer properties of the wind at the comet's location. These inferences complement direct measurements from spacecraft and help extend understanding of solar wind behavior to regions and times not sampled by existing missions. The comet's trajectory through the heliosphere provides a natural probe of conditions at 5 astronomical units during a specific phase of the solar cycle. No spacecraft currently operates at exactly the comet's location, following exactly the comet's path. The comet samples a unique combination of heliocentric distance, ecliptic latitude, and solar cycle phase. The observations, though limited by distance and available instrumentation, add one more data point to the growing library of heliospheric measurements that collectively map the Sun's extended atmosphere. Only took the arrival of one interstellar visitor to provide this unique sampling opportunity. As the comet moves beyond 10 astronomical units, solar heating becomes insufficient to maintain significant outgassing. Water ice, the most abundant volatile, requires temperatures above roughly 150 Kelvin to sublimate at appreciable rates. At 10 astronomical units, solar flux is 1/100th of its value at Earth's orbit, and surface temperatures on a slowly rotating, dark nucleus may fall below the sublimation threshold. More volatile species like carbon monoxide may continue to outgas at larger distances, but production rates decline steeply. The plasma tail disappears first, its visibility dependent on sufficient ion production and excitation. As the ion production rate drops, the tail dims and shortens. The tail's emission fades below detection limits, while the nucleus itself may remain barely visible through reflected sunlight. Eventually, even the reflected light becomes too faint to detect. The comet merges with the darkness, indistinguishable from the countless faint objects that populate the outer solar system and beyond. The dust grains released during the comet's active phase continue their own journeys. Grains ejected near perihelion, when the comet was closest to the Sun, carry the highest velocities relative to the comet. Some of these grains follow trajectories that will take them back toward the inner solar system. Though they will never fall into the Sun or collide with planets, the grains' orbits are also hyperbolic, or at least highly elliptical. Other grains follow trajectories similar to the comet's, receding from the Sun on paths that lead eventually to interstellar space. The timescale for the comet's departure from the solar system spans millennia. At 40 kilometers per second, the comet covers approximately 1.3 astronomical units per year. Reaching 100 astronomical units, the approximate distance to the termination shock, requires roughly 75 years from perihelion. Reaching 1,000 astronomical units, well beyond the heliopause, requires 750 years. Reaching 1 light-year, the distance at which the Sun's gravitational influence becomes comparable to perturbations from other stars, requires roughly 7,000 years. Only took mathematics to project the comet's future trajectory across these vast timescales. During this long departure, the comet will pass through different regions of the heliosphere. First, the supersonic solar wind regime, where the wind flows outward at hundreds of kilometers per second and the Sun's magnetic field dominates. Then, after crossing the termination shock many decades after perihelion, the heliosheath, where the solar wind has slowed but still fills the space and carries the sun's magnetic field. Finally, after crossing the heliopause perhaps a century after perihelion, the local interstellar medium, where the sun's influence fades and the interstellar magnetic field and plasma dominate, the comet will notice none of these transitions. The nucleus, cold and inert by the time it reaches the outer heliosphere, responds only to gravity and to the occasional impact of dust grains or cosmic rays. The comet's trajectory, determined by its velocity and the sun's gravitational field, follows an unchanging hyperbola regardless of the plasma environment through which it passes. The comet is a ballistic object, its path set by initial conditions and the inverse square law of gravity. In interstellar space, the comet will drift for millions or billions of years. Its velocity relative to the local standard of rest, the average motion of stars in the solar neighborhood, is modest, only a few tens of kilometers per second. The comet will take millions of years to cross the distance between stars. During this time, cosmic rays will gradually process the comet's surface, breaking chemical bonds and creating new compounds. Ultraviolet photons from distant stars will continue the processing at a slower rate. Occasional impacts with interstellar dust grains will erode the surface atom by atom. The comet may eventually pass near another star, though the probability of a close encounter within any given million-year period is extremely small. The space between stars is so vast, and the stars so widely separated, that most objects travel through interstellar space for billions of years without approaching another stellar system closely enough to be significantly deflected. The comet could wander the galaxy for longer than the current age of the solar system before experiencing another perihelion passage around a different star. Only took one passage through one stellar system to mark a brief moment in the comet's multi-billion-year existence. The comet carries no memory of its visit. No record exists in the nucleus documenting the solar wind conditions, the magnetic field configurations, the distance of closest approach, or the human observations. The comet is transformed by the visit, slightly less massive, its surface altered by solar heating, its rotation possibly changed by asymmetric outgassing, but these changes carry no information accessible to a future observer about the specifics of the encounter. The comet is simply an object that passed near a star, was warmed, released some volatiles, and continued onward. Human observations of 3I/Atlas will be archived, digitized, preserved in databases that may last for decades or centuries if properly maintained. The images, spectra, light curves, and orbit determinations will be available for future scientists to study, to compare with other interstellar visitors, to use in refining models of comet formation and evolution. These observations represent humanity's brief window into this particular traveler's passage, a window that opened for months and then closed as the comet faded from view. The calm before solar gusts continues after the comet departs. The sun follows its cycle, activity gradually rising toward the next maximum. Solar wind streams continue to flow outward, filling the heliosphere. Coronal mass ejections erupt sporadically, sending shocks and magnetic clouds through interplanetary space. The heliosphere breathes, expands and contracts slightly, rotates with the sun. The structure persists whether or not comets pass through it, whether or not instruments measure it, whether or not humans contemplate it. 3I/Atlas recedes into the outer solar system. An object among countless objects, a visitor departing after a brief stay. The comet continues outward, following the path determined by gravity and initial conditions, carrying its small cargo of ancient ice toward the darkness between stars. The solar wind follows the comet for a time, extending to the heliopause and beyond. Then the comet crosses the boundary and enters interstellar space, where the sun's breath no longer reaches, and the journey continues in the galaxy's quiet cold. Only took one comet's passage to trace the invisible architecture connecting star to interstellar void. The comet drifts outward through thinning plasma. Each day carries it farther from the sun, deeper into the outer heliosphere's stillness. The solar wind weakens, its pressure declining, its velocity constant, but its density falling toward zero. The magnetic field stretches thinner, its spiral geometry persisting, but its strength approaching the threshold of detection. No tail remains. No coma surrounds the nucleus. The ice has ceased sublimating in the cold beyond 10 astronomical units. The comet is now only a small dark object, perhaps 1 kilometer across, reflecting a faint trace of sunlight that takes over an hour to reach it from the solar surface. The reflected light, red shifted slightly by the comet's recession velocity, fades into the background glow of distant stars and galaxies. The heliosphere continues around the comet, a vast bubble extending for decades of travel in all directions. The sun's influence persists through gravity and through the tenuous solar wind still flowing outward at hundreds of kilometers per second. The termination shock lies ahead, decades away. The heliopause lies beyond, marking the boundary between the sun's domain and the interstellar medium. The comet will cross these boundaries eventually, transitioning from one regime to another. Though no observer will witness the crossing, time elongates in the outer solar system. Days become indistinguishable from one another. Years pass without significant change in the comet's environment. The slow recession continues, measured in astronomical units per decade, in hundreds of millions of kilometers per year. The comet's velocity relative to the sun, 40 kilometers per second, seems vast by terrestrial standards, but infinitesimal compared to the distances to be traversed. The solar wind thins to whispers, to echoes, to near absence. Its particles arrive at the comet's location hours after leaving the sun, carrying information about a distant time, a distant place. The wind flows past the inert nucleus without effect, without interaction, without consequence. The nucleus drifts on, cold and dark, patient in the manner of objects that have no choice but patience. Silence spreads through the outer heliosphere, not the silence of absence, but the silence of vastness, of processes so slow and diffuse they approach stillness. The magnetic field oscillates gently. Particles drift along field lines. Cosmic rays penetrate from the galaxy beyond. All of it happens without sound, without hurry, without end. The comet continues. The solar wind continues. The heliosphere breathes,